kids, welcome to yet another wonderful session by Physics Wala. This is Sriraj, your physics tutor for the day. How are you all doing? I hope you all had a wonderful day today, and guess what? We are back with yet another wonderful one-shot marathon where everything will be covered from every nook and corner of your 10 CBSE physics syllabus, and I hope you all are super excited. I know the day was pretty lengthy because you already had attended a previous marathon, and that's the reason in this session what I'm gonna do is I'm not gonna kind of make you write a lot, but instead you can just sit back and relax because you've got exams in just 2 days. So just listen whatever I'm saying, make me your focus, whatever I say gets tattooed inside your brain. Are you all ready? How is the Josh, guys? How are you all feeling today? Hi Prince, how are you? How was your day? Hello Nancy saying, how are you? Welcome to the session. I'm eagerly waiting for you all to kind of join. PayPal, hi there. Prince, it's like PayPal, is it? All right. So within 2 days, the exam is about to come. So how are you? Like, what are you feeling? What kind of emotions do you have? I'm going to give you three choices. Happy, kind of neutral, or I'm a bit frustrated, right? How are you feeling today? How are you feeling today? We've got another person, Nancy Vlogs. Hi there. Welcome to the session. So how too good? Absolutely great. I want this mindset till the end of your exam so that this positive attitude of yours will push you to the greater heights. All right. Shall we get started? Afia says neutral. Right. But you know what? At the end of the session, the feeling of you will be super high. Okay. Payal. Okay, sir. PayPal nahi Payal. Okay. Hi Payal. Okay, so what about me? Well, I am feeling super excited. My energy levels are like super high. Okay, so let's get started. You know what? How many chapters you think we have in physics? 4 chapters, right? So out of these 4 chapters, which do you want me to start first? Human eye, colorful world, light, electricity, or magnetism? I'll start a poll. You can just tell me which we want to start. A, light. B, human eye, colorful world. C, electricity. D would be magnetism. Just say A, B, C, D. Vote. You should give your votes. A, B, C, D. Not 1, 2, 3, 4. A, B, C, D in your chat box. Live chat. Quick, quick, quick. I want you to give me A, B, C, or D in the live chat. So let's get started, okay? We've got so many people in the live chat saying A, B, C, D. Okay, let's see. A is light, I said. B is human eye and colorful world. C is electricity. D is magnetism. Whatever chapter gets the more votes, I'll be starting with that. Do not worry, everything will be covered, but starting depends upon what you are voting. Alright? So guys, quick, we're running out of time. Just give me your answers super quick so we can get started. Okay. Right, we've got like 10 more seconds, guys. I can see many of you voting for D. Shall we go and look at the results? Okay. Okay, if you can see here, B and D are tie. Guys, now you're making this super hard for me. B and D are tie. You want human eye or magnetism? Last chance. Between like second and fourth chapter, one last chance. Okay, I get to see many of you are asking magnetism. Shall we start with magnetism? Are you all ready? By the end of the session, I'm going to make magnetism so easy. You would say, all right, sir. All right, I'm so happy with the magnetism. Okay, let's start with magnetism. Based on your request, I'm starting with magnetism. All right. Okay, then. Let's dive deeply into the magnetism itself. Okay. Magnetism, magnetic effect of electric current. All right. Chalo then, let's start. This is magnetic effect of electric current, okay? It is written as magnetism, but what's this? Magnetic effect of electric current, okay? This is your chapter 4, my dear students. This will be your chapter 4. And what does this say? Magnetic effect of electric current. Let me just quickly write it on the board. Magnetic effects, okay, of what? Electric current, right? Current, okay. Right, let's get started. Sure. Hans Christian answer, right, we're going to look about that as well, okay? Now, starting to talk about the basic stuff itself, what magnets are. So magnets are something which attract other magnets or magnetic materials that That's what we're going to call it as magnets, right? So magnet comes in different shapes. We've got bar magnet. We also have got ring magnet. Ring magnet is in the shape of ring, right? So what about this? A cylindrical one, the one which is in the shape of cylinder. This is horseshoe magnets. So this is basic things about magnets, all right? Now, what exactly are magnets? You all know, right? Magnets are those which attracts magnetic materials like it can be cobalt, nickel, or it can also attract what? Another magnet. So this is basic stuff about magnets. Talking about magnetic materials, right? So the magnetic materials can be many other things. For example, we've got iron screw over here, nickel coin, and a steel paper clip and a steel spoon. They all get attracted by magnets, right? They gets what? Attracted, right? Attracted to a magnet. So that's why we call those are magnetic materials. What are non-magnetic materials? Okay. Now, non-magnetic materials are those which do not get attracted by magnets. Okay. Electromagnetism, the relation between magnetism and electricity, great. So it's like magnet because of electricity's magnetic effect of electric current. Nicely said, Shiva 369 Sky. Right. Now, talking about basic things about magnets, all right? Magnet has got two directions. Well, this is like one shot last final revision where you have to see everything. So we'll be running. What happens in marathon? You'll be running right till you reach your goal. So that's what we'll be doing today. Okay. So now, as I said, magnets will be having how many different poles? We'll be having two poles. What's first one? First one is North Pole, and North Pole is usually represented in what color? That's red color. What about another pole? Yes, the next one is South Pole, that is represented usually in blue color. Okay. Now, talking about how magnets attract or repel. See here, if you have two magnets with you, let's say you've got how many magnets with you? Two magnets, okay? First magnet is having north over here, and second magnet is having north over here. And you know, south is represented in which color? It's in blue color, right? And south is over here. Now, if you see here, what is happening? Two like poles are facing each other. Now, do you remember what happens if two like poles are there? Here it is south, south. Now, like poles repel each other. Remember what you have studied, right? So, one thing you learn over here is like poles repel, right? Repel means they go away. Like poles go away. Now, what if you had one north and one south? They get attracted. So, the unlike poles attract, right? So, and guess what? There is one more point what you should know. Magnet cannot exist with a single pole. Sir, can I expect a magnet with only one pole, only north or only south? No, it's not going to happen. So, magnet means it will be having two poles no matter what you do. Even if you try to cut it in the half, of course, we're not going to get two different poles. Well, equally, the north and south poles gets divided into these magnets. Got it? Great, Siva. He says like poles repel and like poles attract. What you said is absolutely great. Now, unlike poles attract each other while like poles repel. As I said, here what is happening? Like poles are there and they are kind of repelling each other. Okay. Prabhakar says, sir, please cover everything. I'm dedicating my crucial time to watch. In fact, guess what? Whoever is kind of watching this session are going to score more than 95% in physics. No doubt about it. Okay. So let's get to the next part. Next, talking about natural and artificial magnet, I'm not going to spend lots of time here because very small number of questions will be coming over here. Well, natural magnets are those which are available in the nature like lodestone and ferrotite. And talking about artificial magnet, which we will be doing and discussing pretty soon. Now, how did people sail in the olden days? Well, that's because of magnet itself, okay? The earth behaves like a big giant magnet. Inside the earth, we have molten metals. We've got lots of electric current because of that. So it creates a big giant magnetic field around it. Now, when you try to kind of align a compass, so what's going to happen? As I said, unlike poles attract, right? So if this is the south pole of the earth, your north pole will be kind of directed towards the south pole of the earth. So it's, if you're going straight to the north of your compass, you'll be reaching the geographical north. And remember, you might have seen this, right? So the geographical north is magnetic south. Why is it like that? Before they discovered Earth is a giant magnet, there was already geographical north and south. Clear? So imagine you have a compass with you. Compass is showing north. So if it is showing north, maybe our compass is attracted to south pole of the Earth. So if you're going like this, you'll be reaching where? Geographical north. Clear? I hope this is clear. Now let's go to the next part, which is very important for us. Region of influence, that is magnetic field lines. Okay, now what is magnetic field lines, sir? Imagine you have a magnet, the region around a magnet. Okay, what's magnetic field lines? It's just a region around a magnet where if you bring another magnet, it either attracts or repel. Got it? Is it clear, my dear students? I hope that's clear. So what is region of influence? It's a region, okay? It's a region around a magnet, where if you bring another magnet, it gets influenced, whether it can be attracted or it can be repelled. Is it, are you able to understand? Is it clear? I hope this is clear, my dear student. What does magnetic field line says? Magnetic field lines, it's a region, okay? See, imagine you've got a north pole over here. How does north pole look like? This is the north part of a magnet. What does the magnet has? Magnet has the south pole. Now, if you try to bring another magnet, let's say you are going to bring a small magnet over here, okay? There is a magnet over here, and the magnet also has south pole, and magnet also has north pole. What's going to happen? We have got unlike poles over here, right? So unlike poles, they are going to get attracted here. They are attracted. Okay, let me just take a color so that's visible. Okay, attracted. So this is what is, my dear student, is the region around the magnetic field. Okay, so the region of influence is magnetic field lines itself. Okay, so this is what we say, the magnetic field lines. They are imaginary lines. Very good, Harsh. Whatever you said is right. They are magnetic field lines. Okay. Prince, yeah, whatever you said, we are going to discuss about it. Just wait and watch, okay? Now, see, if you have magnet like this, the field lines will be somewhat like this, okay? So, if you keep another magnet, the other magnet gets attracted. Sir, for how many marks can we expect this question? Well, you can definitely expect a question on this for, guess what, 3 marks. If they ask you for 3 marks, you'll be just listing the properties which we are going to discuss. But if this is for 4 marks, okay, 3 or 4 marks, what are we going to do? We're going to draw the magnetic field lines along with the explanation, okay? Now, region of magnetic influence is just like magnetic field lines around a magnet, okay? These are magnetic lines around what? Around a magnet. Do you think there will be magnetic field lines actually existing? They are imaginary, okay? So yeah, 4 marks is a lot, but still you might also get it because you're drawing it and you're explaining it, okay? Now, talking about different properties of magnetic field lines. See, the magnetic field lines will be kind of like this, okay? Now, they are, first of all, I said they are what? They are imaginary lines. You already know that. Now, what's the direction of that? What's the direction of magnetic field lines? You all know the direction of magnetic field lines. They originate from north, they end at the south, right? Can you see this? Let me retrace it. See, this is the north pole, right? Now, can you see it? This is north, this is south. How the magnetic field lines are coming? They are coming out of the north pole, right? They are emerging out of north. And where are they entering? They are entering the south pole. Got it? So it's like and exiting from north, entering south. Is it clear? I hope everyone are able to relate this. Now, this is done. So the north pole to south pole outside the magnet. But what happens inside the magnet? Before that, we have one more point. You'll be writing this point whenever they ask you. The magnetic field lines acts as a continuous closed loop. Loop means what, my dear students? Okay. Now, let's say we have a magnet over here. There is a magnet. This is north pole and we have a south pole. How does the magnetic field lines will be? It will be from north to south. Okay, sir, that's done. You have said that. But you also said that's a loop. This is how a loop looks like, right? Loop is a closed path. For a closed path, if the magnetic field lines are from north to south, this is outside the magnet. Inside the magnet, what should happen? to complete the loop, it has to be from south to north. So this is how it will be, right? This is inside the magnet. I hope you are able to relate it. See, outside the magnet, it is like this, north to south, north to south. To form a complete loop, it should be from south to north inside the magnet. I hope you are able to understand. Yeah, they are a closed curve. Now, what about at the poles? Can you see? This is a pole, right? Now, if you can see here, this is one pole and this is another pole. Near the poles, magnetic field lines are so stronger. Okay, so the magnetic field lines are stronger at the poles. So you can see the density of the magnetic field lines. It is more, right? It's denser near the poles. Okay, so the magnetic field lines are pretty denser near the poles. So this is what we say. Thank you. Now going to the next part. Field lines do not intersect. Can you see any field lines intersecting here? No, they do not. Why they do not intersect? Because now see here, they might also ask you a question, why field lines does not intersect. Okay, intersection means two different directions. Okay, two different directions at that point, at the intersection, which is not possible at intersection. Do you think that's possible? No, right? If the field lines are from north to south, there's only one direction from north to south, so it won't be kind of intersecting each other. Is it clear? If you write this much, you'll be getting easily 3 marks along with the diagram. I hope you all grab these 3 marks. Okay, now going to the next part. See, magnetic field lines properties, they might ask you for two different things, like a bar magnet, whatever we discussed. But imagine you have two different magnets. So here the field lines are parallel to each other. Okay, so they're not gonna kind of intersect each other. They are same at every point. This is not a bar magnet. They might ask you for a bar magnet. This is what? This is a bar magnet. Okay, they won't just ask you what are the properties of magnetic field lines. They will ask you the properties of magnetic field lines of a bar magnet. So you should be able to differentiate. Okay, in bar magnet we'll be having the field lines emerging from where to where? From north to the south. See here, north to south has changed here. Why? They flipped the magnet. It's not always left or right, it's north to south. Remember, even here, see, north to south. Okay, here also north is red color, south is, here it is blue color. So this is the direction of magnetic field lines. Okay, they do not intersect. They are very denser at the poles. This is pole, right? This is north pole, this is south pole. You can see many field lines are there. They are pretty denser at the poles, but rarer, right? Apart from that. Okay, as you move away from the magnetic field lines becomes less denser and denser. Okay, I hope this is clear. Yes, great. I like super interaction. I know you're tired because of course you are listening to other marathons and exams are running. So let's just keep some focus over here. Okay, so this is about magnetic field lines, my dear kids. This is there no such an important concept. Why is this important? Hans Christian Oersted. This will be asked in your exam. The highlight of magnetic effect of electric current. Without this, the chapter is not done, right? So what does this say? Well, there was a scientist who kind of was making an experiment where he observed whenever you take a battery, connect some wires to that. So what's going to happen when you connect a wire? Electricity flows, right? So when you kind of connect wire to this, what happens? We get to see electricity flowing. See, electricity is flowing everywhere. So what is this? This is current, right? When the current flows, what happens? When the current flows, there will be magnetism around the magnet. There will be magnetic field around the magnet. That's what has been discovered by the famous scientist Hans Christian Oersted. This is, what does that say? Current produces magnetic field around it. Let this be a conductor or anything. When a current is passing in a conductor, it produces magnetic field around it. Shall we write it down? Are you all ready? Yes. So current carrying conductor, you know, current carrying conductor, what does that do? Conductor produces magnetic field around it. Okay, produces magnetic field around it, okay? Magnetic field around it, okay? We're going to talk about how this magnetic field will be as well. Well, these magnetic field, because of the current carrying conductor, forms concentric loops. How does it look like? Well, here it comes, okay? Now, as I said, sir, you said that whenever we have a current carrying conductor, they'll be having magnetism. How can we prove that? Is there any proof? Yes, in fact, we have a proof. Now, bring a compass, magnetic compass. So what does that do? Whenever the current is actually flowing, the magnetic compass deflects. When does this deflection happens? This deflection will be happening only when there is another magnetic field, right? So you might have played with this, right? Take a compass, take a magnet. You can kind of just make the magnet inside the compass roam, right? So the same thing is happening here. Because of the current flowing, this compass deflects, okay? Shall I write it over here? What is this? This is a magnetic compass. This magnetic compass deflects, okay? This magnetic compass deflects because of the current which is flowing in the wire. So what can we conclude? So there must be another magnetic field because of a current carrying conductor. So a current carrying conductor produces magnetic field around it. So this is what is Oersted experiment concluded, okay? Very good, Siva. So right hand thumb rule. So how does this magnetic field lines will be? So you said the magnetic field lines are there, but how it will be? Shall I write how? How will be the magnetic field lines? Well, the magnetic field lines will form a concentric circles. What does concentric circle means? A circle with one center, different radii. Okay, sure. So this is what we call concentric circle. Guys, I am here to help you all. I'm here to kind of support you all for the exams. Yeah, I'm gonna pray for you as well. Chalo, let's see how does this magnetic field lines will be. They form concentric circles, okay? They form concentric circles. What are concentric circles? A circle with one center and different radius, right? One center and different radius is what we're going to call it as concentric circles. So this is how magnetic field lines because of a straight current carrying conductor will be, okay? Now see here, at the center we will be having a wire, okay? If you see from the top, the magnetic field lines forms concentric circle, okay? Shall I write it over here? I'll erase the part how and how it will be. The magnetic field lines will be concentric circles with wire at the center, with the current carrying conductor at the center, okay? Harshad is asking, sir, from which state are you? I'll be telling what are languages I know you can guess. I know Hindi, I know English, I know Kannada, and I know Telugu as well. Now guess what state I might be from. Okay, now guys, so see, field lines form what kind of circle? Concentric circle. How does concentric circle look like? Concentric circle will be having one center and different radii, right? Siva guessed it right. I'm from Bangalore. Great. Okay, now, so what is the direction? How can we even find it? You just gave me half information. Now, how can we find it? Well, imagine you have a wire, okay? And the current is flowing like this in this direction. So how will be the magnetic field lines? So the magnetic field lines that can be found out using a great rule given by the scientist, and the name of the rule, can you guess it? Right hand thumb rule, okay? What's the name of the rule? The name of the rule is right hand thumb rule. The right hand thumb rule says whenever you point the direction of your thumb in the direction of flow of electric current, the fingers which curl around it will be giving you the magnetic field. Is it great? Okay, Harshad, I get it. Where are you from? I just got it, okay? Now, the magnetic field lines are kind of forming concentric circles whenever you are going to use your right hand where the hand is pointing in the direction of flow of current. Sir, how can we draw that? Okay, whatever doubts you have, Rash, you can just post it, okay? Post it in the live chat. I'll be able to answer that, okay? So it says that imagine a current is flowing in upward direction, okay? Current is going in the upward direction. You're going to only use right hand, no left hand. Direct in the, point the right hand thumb in the direction of the flow of current. Prabhakar, here the thumb shows the direction of current. It's not like refers to what? You're aligning the thumb, okay? Is it clear? See, if the current is going in the up direction, you're pointing the thumb in the up direction as well. What happens to the finger? The finger which curls around it, gives the magnetic field. Sir, how to draw that? Very simple, my dear students. How to draw that? They are a concentric circle, right? They form concentric circle. Here is one circle. Here is another one. Here is one more. Here is one more. So this is how the magnetic field line looks like. Is it clear? Is it clear, my dear students? I hope you all are understanding what I'm saying. Where? What is this? I is current carrying conductor, okay? Current carrying conductor, okay? Is it clear? And what about this? This thing is magnetic field lines, okay? The concentric circles, these are field lines, okay? Field means magnetic field, okay? Field lines. So this is how it works. So this is about the right hand thumb rule. They will ask you for how many marks. They might ask you 2 marks. State right hand thumb rule. Will you be able to do it or not? I believe you will be able to do it, okay? Whenever they ask you to state right hand thumb rule, you'll be see, the important points over here is that for a straight wire, the magnetic field lines are circular around it. What kind of circle? They are concentric circle, okay? The field lines are, what kind of circles they are? They are concentric circles, okay? They are concentric circles. So if you write this much, you'll be getting marks, okay? So you'll be writing what is right hand thumb rule, where do we use it, and the diagram, done. You will be getting complete marks. Is it clear? I hope this is done, my dear kids. Shall we go to the next part? Okay, going to the next part where we'll be talking about a small experiment, okay? How does these two conductors behave, okay? Shall we do it? Using the right hand thumb rule, we are going to decide this, okay? Rajat, hi, hello there, how are you? Okay, next, let's talk about magnetic field lines. Now see here, how is the direction of flow of current? The current is going in the upward direction. Can you see what is the direction of flow of current? The current is going in upward direction. What about here, my dear students? Here also the current is going in upward direction. Okay, sir, done. What is your question? Well, let's try to apply right hand thumb rule here. Shall we apply right hand thumb rule? Whenever, okay, let's see, okay. Now the question is pretty simple. Of course, we know because of current there will be magnetism, but will they attract or will they repel? That's the question. This kind of application based question will also come in boards. This might also appear in where? Boards, okay. You might also expect this kind of question in boards, all right. So let's see how to do this, okay. Right hand thumb rule, what does that say? So point the direction of your right hand in the direction of what? Flow of current. Okay, sir, current is going in the upward direction. How will be the magnetic field lines which curl around it? So this is how the magnetic field lines will be. Correct. Whatever you said is correct, okay. Let me draw one more magnetic field line. Okay, now how does magnetic field lines will be? Yes, fingers are wrapped, okay. The magnetic field lines will be entering the south pole, exiting the north pole. Remember, here I said, do you remember? If you see here, I said it comes out of north, exits where? South. It comes out of north and exits south. Similarly, in this question, if you see, it is magnetic field lines are entering here, it enters and it exits outside. It enters here, exits outside. So if it is entering, this has to be south, and if it is exiting, this has to be north. Is it clear? I hope this is clear, my dear students. Now comes the next part. Here also the current is going in the same direction. So kind of what happens? The magnetic field lines will be forming concentric circles, because that's what right hand thumb rule says, right? Now talking about this, the magnetic field lines are entering over here. So this would be our south, okay. And what about this? It is entering south, exiting, this is north, okay. This is north. Now can you see one north, one south is there? This is south, this is north. Are they like or are they unlike? Like poles or unlike? Like they attract each other. Very good, Prabhakar. They attract each other, okay. They attract each other because they are unlike, okay. Hi Aditya. F says Hi, hello there. How are you? Welcome to the session. Okay, great. Shiva and Prabhakar, you're saying the right answer. They are unlike and they are going to attract. Hats off to you. You will be able to get complete marks if this question is asked. Shall we go to the next part, my dear students? Yes. Okay. Now comes the important part where we are going to discuss magnetic field because of a circular loop. Why is this important? This is important because you are going to understand the concept of solenoid based on this, okay? Nancy also says unlike. Great, my dear student, whatever you said is correct, okay? Now, see, why are you able to understand this? If you understand, see, if you kind of know this, if you know this, solenoid is easy. Solenoid, understanding solenoid is super easy, okay? Super easy. So that's why we should know this. I want complete focus. I need complete attention of yours so that we are going to discuss this part in detail and you will be telling me, sir, I understood. I will be able to do the solenoid super easy. I hope you're ready, okay? Sir, confirm question in board, solenoid is my prediction. Yes, based on previous analysis, solenoid is asked in each and every paper, 99%. So this time also they'll be asking you, okay, there will be in fact, indeed, gonna probably talk about solenoid, so carefully listen, okay. To understand solenoid, you should know something about how magnetic field will be due to circular current carrying conductor. So let's draw two conductors. You have one over here and you have another over here, okay. Now, what does right hand thumb rule says? I mean, what does Oersted experiment says? Whenever you have got a circular conductor, what does that do? That also help, that creates magnetic field around what? Around a conductor. Now, what kind of magnetic field will be there? That is based on right hand thumb rule. Shall we apply that? Okay, I hope you are all ready to apply right hand thumb rule over here, okay. Now, I am going to break this into some parts, okay. I'm going to break this into certain parts, okay. Just give me a moment. I'm going to kind of break this into certain parts, okay. So I'm breaking the wire. Why am I breaking? You'll get to know, okay. So this is a circular current carrying conductor and I've made 4 parts, okay. Can you see? We've got 4 parts of it, okay. So we've got 4 parts of it. Here also we've got how many parts? We've got 4 parts of the wire. Now, sir, how the current is flowing. In one, I will be taking the current going in clockwise direction. In the other case, I'll be taking it in anti-clockwise direction. Okay. So now, see here in the first case, this is, imagine this is a circular coil. We have broken it down. Okay. So current is going in clockwise direction. How is the current going, my dear students? The current is going in clockwise direction. What is clockwise direction? Clock, however it ticks. Can you see how clock ticks? That's clockwise direction, okay? I hope you understood how the clockwise and anti-clockwise works. So clock goes like this. So current, let's say the current is also going in clockwise direction. Okay, sir, fine. You said it and we have considered it. What now? Now, we'll be applying right hand thumb rule to analyze where we'll be getting south or north. Shall we do it? Are you all ready? Let's get started, okay? Now, if you see here, the current is flowing in the downward direction. See, this is how the current is, right? So if the current is like this, it enters here and exits outside. It enters here and exits outside, right? So where does it enter? It is entering inside. So we'll be having what influence? South here, because it is entering and exiting outside. So we will be having south here, north outside. Is it clear? Okay. Next, let's talk about this. Can you see here the current is flowing like that and the fingers curl around it, right? So the current is going, it enters and exits outside. Exit is north, entering is what? Entering is south. Clear? The same thing happens in 2 other parts as well, okay? Here the current is going in this direction. Point the thumb in the direction, okay? So if you point this will be what? This will be south and the other part will be north. Similarly, here we have north and inside we have south. Is it clear? Is it clear? What did we just do? We had applied right hand thumb rule for the different parts of a wire. Now, in this case, what happens, sir? Can you see inside we have south? So we can easily conclude that in the case of clockwise direction, whenever the current is flowing in clockwise direction, the middle part will be having south influence. Okay, shall I write it down for you? So we had south poles everywhere, right? So we'll be having kind of south pole in the middle. Okay, so how to remember, sir? Well, you can remember, this is how you write. Okay, so the current is kind of flowing like this, right? This is how the current is flowing. So you can imagine this is how it happens. So shall I write it on the screen? This is for clockwise. Okay, let me reduce the size of the pen. This is clockwise. Okay, clockwise flow of current in a circular current carrying loop. Now, sir, shall we take anti-clockwise? Well, definitely. Okay, hi Aditiraj, how are you? Welcome to the session. I said welcome to the session. Let's focus. Okay, how are you doing? Prabhakar is there in the session. Many others are there. Okay, so welcome to the session, Aditiraj. Okay, now coming back to here, the current is flowing in anti-clockwise. Anti-clockwise means this is how it flows, right? Clock ticks like this, but here it is happening in the anti-clockwise direction. Is it clear? Is it clear, my dear students? Right, sir? That's absolutely clear. Shall we see where and all we'll be having north and south pole? Well, definitely, my dear kids. Now, if you try to apply the right hand thumb rule on the different parts of a wire, what happens here? The current is going up. So it is, if you apply right hand thumb rule, the fingers which curl around the wire will be giving you magnetic field, right? Now, if the thumb is pointing in the direction of flow of current, it is entering. So this has to be south, right? So this has to be south over here. Now, inside what happens? It exits, right? After it enters, it has to exit. So here we have north. I hope this is clear. Now let's see what's going to happen. Okay, now here the current is going downward. So right hand thumb rule says what? The direction of flow of current. The thumb is in the same direction. It enters here. So if it is entering, it is south. Wherever the magnetic field line enters, what did I just say? That's south, right? So where is it exiting? It exits. After it makes a turn, it has to come from inside. So north is there in the middle. The same thing happens for the two other parts, and we can say we are having north pole in the middle for anti-clockwise direction. Whenever the current is flowing in anti-clockwise direction, at the middle we'll be having the north influence, right? Behind that you'll be having south influence. Clear, my dear students? I hope this is clear for you. So can you tell me, okay, this is for anti-clockwise, okay? This is for anti-clockwise direction of flow of current. I hope this is clear. Yes, everyone agrees with this. For clockwise, flow of current is in clockwise direction for a circular loop. See, this is current carrying loop, and how does this loop is? Loop is a circular coil. Okay, now circular coil, if the current is anti-clockwise direction, in the middle we'll be having north. You know, if seen from front, okay, if the current is going in clockwise direction, we'll be having south. Is it clear? I hope everyone you understood. Why is it required to know about magnetic field solenoid? Okay, sir, explain clockwise rule. This is what, my dear students, see here, clockwise rule, using right hand thumb rule, we have concluded if the current is going in the clockwise direction, at the center you get to see south. Behind, of course, you'll be having north. Similarly, if the current is flowing in the anti-clockwise direction, what happens? At the front, you'll be having north pole. Clear? I hope this is clear. Yes, clockwise, you'll get to see south influence from the center. Backside, you'll get to see north. The same thing happens over here. Clear? Okay, so going to the next part. Okay, so what does the next part says? Magnetic field due to a current carrying loop. So this is solenoid. How much important is this, sir? Super important. It has been asked for so many times in all the boards. Okay, yes, I will be taking full physics. Joy, yes, definitely I'll be taking full physics. Okay, now what is a solenoid? We are going to talk about solenoid. Okay, well, solenoid is a circular current carrying loop. Okay, now if you have a circular loop wound in the shape of a coil twister, that's what we're going to call it as what? A solenoid. Solenoid is a helical structure which kind of forms a circular coil. Okay, Now let's talk about this. Okay, solenoid is a helical structure. A wire, a wire wound in the shape of coil, okay, or you might also say that's helix, all right, or helix. This is what we call it as what? A solenoid. Is it clear, my dear kids? Okay, now, so how does it look like actually, right? You take a coil, you wound it like this, okay? You take a coil and you wind it like this. This is how a solenoid looks like. Sir, when solenoid becomes electromagnet, we'll get to see soon. Yeah, indeed, right, Shiva. This is forming a continuous loop, okay? Now, right, so how does solenoid act as an electromagnet? You'll be having a question, right? How does a solenoid might act like an electromagnet? Okay, let us understand how solenoid act as an electromagnet. Okay, how solenoid acts as an electromagnet. Okay, electromagnet. Guys, this is very important. I want complete focus. Yeah, it is just like a bar magnet, slightly different, right, Shiva? But let's understand. Okay, now imagine you have a solenoid. Okay, how does solenoid will be? I'm kind of of course, if you wind it on top of something in the air, it will come out, right? I'm taking something, so it will help me wind out. Okay, now I'm taking something and I'm going to wind on top of this. So this is how winding looks like. It goes and it comes from behind. See, whenever you wind it, try to do it in this way so it would be easier. Do not just randomly draw this. It's a 3D structure. It can look like anything, right? The 3D structures drawn on 2D might look differently for two different people. So try to do this, okay? Kriti Agarwal, when electricity passed through it, yeah, you're right. When electricity passes through this acts like a solenoid, okay? Now, I'm going to draw like this. It goes behind, comes from the front, right? This is how it looks like, okay? This is how it looks like. So, I'm trying to draw a solenoid. Now, when does it act like an electromagnet? When you apply supply to this. Got it? So, let's apply a battery or a supply. So, the current flows through this, okay? A current is flown through this coil. Why? Because that's when the magnetic field lines will be, right, my dear kids? So a current flows through this. Now, sir, can we apply the clockwise rules what you taught? Yes. Shiva, is this a bar magnet? No, it's just a support, okay? Inside we do not have bar magnet, Shiva. Got it? Inside, yeah, it can be anything, okay? It's just a support, okay? It's a support to hold the wire, the coil, I say, okay? It's just a support. Do not think of anything else. It's just a support. Talking about it, we'll talk, okay? Right, great, okay? Now you have it. See, current goes up, flows down behind. Again goes up in the front, flows down behind. Goes up, and it flows down, right? Is it clear, my dears? Okay, support means, example, see, if I take a charging wire and wind it, okay, will it stay here? No, right? It will fall. To create a support, I want something in the middle, right? To maintain the shape. That's what support is. Is it done? Clear, Prabhakar? Is it clear? Okay. To hold the coil, that's what it is. Okay. For now, yeah, it can be anything. It can be anything. Okay. Now, talking about this, how does the current goes? The current goes like this. Backside comes down. Again, it's a roller coaster because it's like what? It's like a coil, right? Okay. Now, it can be, for now, imagine that's a conductor, okay? It's a copper core. I can say, okay, for support, it's a copper for now, okay? It's, or I can say iron. It is iron, okay? It's iron bar, okay? Hold for support. Is it clear? Okay, it's a iron, okay? Now, talking about it, see here, if you see from this side, if you see this part from this side, the current is going up. Right side, the current is going up. Left side, the current goes down because it's a circle, right? It's a loop. So the current is going up in the right side, and the left side, the current is going down. So how is it? Is it clockwise or anti-clockwise? See, right side, this is my right hand. Right hand going up, left hand going down. So this is anti-clockwise, right? So what did I say anti-clockwise? Do you remember? Anti-clockwise, what do we have? We have north pole. Remember, my dear students? So what kind of influence do we have here? Here we have north influence. Okay, sir. Okay, fine. I agree. What about this side? Here, if you see, the current is going up in the left side, and that side down the current is going, right? It is going up in the left side, and in the right side it is going down. So how does it look like? It's a clockwise. See, right hand, I mean left hand going up, right hand coming down. It's a clockwise, same how the clock ticks. So what kind of pole we might have here? We have south pole. What is it? We have what? South pole. Is it clear? I hope this is done. Any doubts how this acts, like how solenoid acts? What are the poles we have? Is it clear, or you have any doubts? Okay, I hope this is clear. Now talking about magnetic field lines. Okay, is it clear? Just tell me yes or no how magnetic solenoid works like. Now, okay, thanks a lot that you said it is clear. Now see, magnetic field lines will be from where to where? From north to south, right? From north to south. From north to south. This is how you are going to draw a solenoid and you are going to understand. Aditya Dubey says once again, yeah. See, I wanted to explain this in another way, which I will explain now, okay? Solenoid to understand using a different rule, okay? Solenoid. I'll explain in a different way. I want everyone to focus now, okay? Now, guys, look. How does solenoid look like? So, to wind a wire, I would require one support. So, I'm going to take a core. This is how the magnetic field, this is how the winding is. But here, what I do is I reverse the supply. See what I'm going to do. Reverse the supply. Last example, positive was this side. So current was flowing like this. But now, here I have reversed it. So the current will be flowing like this. Is it clear? Okay, now is the time where you focus, okay? Now, the current is going up and then behind it goes up. At the front, it comes down, right? So this is out. Behind goes up, front, it flows down. I hope this is clear. Now, sir, how to apply? Is there an easy way? This is okay. This is a bit easy, but we used clockwise rules. What rule is used here? We used clockwise rule. But is there any other easy way? Yes, there is another easy way. Shall I tell you the easy way? Now, the easy way is right hand curl rule. Very easy, okay? Now imagine how the current is flowing. The current is flowing downwards, right? The current is flowing downwards. Use your right hand and you show how the current is flowing using these four fingers. Thumb will be giving you north. First I will write and let's verify using clockwise, okay? So this is north. So if this is north, what about this, sir? This will be south. How did I do this? I just aligned my fingers in the direction of flow of current. See, the direction of flow of current is downwards. This is how it is. So the thumb will be giving me north. Similarly, here you see this. The direction of flow of current is upward. Can you see? The current is going up, right? So the fingers are in the upward direction. The thumb will be giving you north. Is it easy? Which one is easy? Right hand curl rule or clockwise rule? Which is easy? You tell me. Okay. Yes. Which one is easy? You will be telling. Last minute master, right hand thumb rule. Well, it's right hand curl rule, my dear. Okay. Now, shall we verify the right hand curl rule using thumb rule? Yes, sir. Both are easy. Great. Let's verify. Okay. Now, if you see here, the current is going up from the backward and it is flowing from this left, right? It is like this. It's anti-clockwise. Over here, it is anti-clockwise. So what's going to happen? Here we have got north. Sir, over there what happens? Here if you see, backside the current is going up. Right side it is coming down. It is clockwise, right? It is clockwise. So clockwise it's south. So you can use either right hand thumb rule. I mean, you can use curl rule or you can use clockwise or anti-clockwise rule. Okay, clear? I hope everyone understood how to apply. Okay, two things you can apply, either right hand curl rule or you can use clockwise or anti-clockwise rule. Clear, my dear student? If it is clear, go ahead and mark your attendance by clicking on that like button. So I'll be seeing how many of you are attending. So it will be from north to south. See the direction of magnetic field lines. It will be from north to south. Yes or no? Yes or no? I hope this is clear. Okay. Prabhakar, Kriti Agarwal, Ashish, everyone, you can say whether it's clear or not. If you have doubt, you can easily ask me. If you don't have doubt, of course, we can just move to the next part. Okay. Yeah, is it clear, my dear students? Okay, so either you can use clockwise rule or you can use right hand curl rule. Okay, I just taught it. So that's about it. So going to the next part. Thank you for giving me the confirmation that it's clear. Going to the next part. See, well, this will be very important. The reason is it is asked in many boards. Okay, many times this was asked in board exams. Okay, boards. Okay, it was asked like more 99% of the time it was asked, because this is the highlight of the chapter. So kind of have some attention where you will be watching this. Okay, clear? Right. Next, I have got a poll question for you, but before that, see, magnetic field lines form a loop, right? Field lines, you know, field lines form a loop. So if they have to form a loop, so inside it will be kind of parallel. Okay, from inside it will be south to north, outside it will be from north to south. Is it clear? Okay, now you have got a pole. Now how does the magnetic field line will be in the solenoid? I just said, see, magnetic field lines in the solenoid will be kind of course they cannot intersect, they has to be parallel, right? And it will be from south to north. Clear? Yes, here comes the pole, and the pole will be for 60 seconds. Here starts the pole. Read the pole and give me the answer. Magnetic field line inside the long solenoid. How will be the magnetic field lines inside the long solenoid? A, B, C or D? Quickly give me your answers, and we will be going to the next part, and leaderboard will be shown. We can flaunt it. Okay. See, the magnetic field lines inside a long solenoid. It's inside, not outside. Okay, it's inside and not outside. Remember, the magnetic field lines inside the solenoid. I just showed you. This is how it will be inside a solenoid. So go ahead and quickly give me your answers. A, B, C or D. Such question, of course, multiple choice question. Why you couldn't expect it? Of course, you can expect it, right? Yes or no, my dear students? Okay. Yeah, time is up. Of course, inside it has to be straight and parallel to the axis, right? See, what is an axis? Axis which is drawn to the perpendicularly to this, right? So option C is right answer. Let's see how many of you have given the right answer. 71% of you have given the right answer, and here we have got top 5 students. We've got Siva, Indu, Anup, Sanjana, Bhargavi and Nancy Singh. Hats off to you, top 5. I will be showing you the leaderboards every now and then, and you can just flaunt it in your social circle that I had attended the class and have got very good position in this part. Okay, clear? Now going to the next part. See, this is what the conclusion. So what does the conclusion says? Now, if the magnetic field lines, okay, this is what is a circular loop, right? And if the current is flowing in clockwise direction, this is what clockwise direction, we will be having south influence in the middle. But just in case if the current is going in anti-clockwise direction, anti-clockwise means this is how the current is going. So in the north pole will be there at the center. Is it clear? I hope this is clear. Sir, why not option A? See, magnetic field lines, they're talking not entirely, instead they're talking about inside a long solenoid. Okay, it's like they're talking about which is inside. Okay, which is inside. Okay, so they are parallel to each other. Okay, now talking about the next part, how did we find this? We used, this is clockwise rule. Okay, so what is this? This is clockwise rule. Why do we use clockwise rule? To determine in a circular current carrying conductor how the magnetic field line will be. If it is clockwise, in the middle we'll be having south. If it is anti-clockwise, we'll be having at the middle north. Okay, so what says? This is anti-clockwise. Okay, anti-clockwise. Okay, clear? Now you can also use right hand curl rule to tell where the magnetic north is. Okay. Well, I hope this is clear. Why did we use this? Why did we understand this? Yes, we have kind of understood this with the to help you understand the solenoid. Okay. What a coincidence, says Bhargavi. Okay, right. Okay, let's go to the next part. Okay. Now, my dear students, one more thing, right? So, solenoid, whenever the current flows in a solenoid, that's when we get to call it as an electromagnet. Okay. Thank you, Prabhakar, for saying crystal clear. I am so happy that you're able to understand. Okay. Sure. So, what is an electromagnet? When the current flows through a solenoid, okay, a current, when a current, okay, when an electric current flows through the solenoid, okay, what happens? Flows through, okay, it flows through a solenoid. What does that do? Solenoid, it acts as an electromagnet. It acts as an electromagnet. Okay, electromagnet. Sir, what happens when I switch it off the power supply? So what's going to happen when you switch off the power supply? Okay. So when you try to kind of switch off the power supply, no more current is flowing and no more magnetic field. Okay. Right. Sir, I feel the loop more hard than solenoid. There is no need to be so be feeling hard about it. It's very simple. Clockwise, anti-clockwise. That's it. Okay. Sir, what issue you're having? Right. No magnetic effect. Right, Shiva. Whenever we turn off the current flowing in the solenoid, there won't be magnetic field. Okay. Now support becomes magnet, sir. Yeah, very good, Prabhakar. Right. We're going to talk about it. We're going to soon talk about it. Let's have it. Okay. Now, so magnetic field around an electric solenoid resembles what? It resembles a bar magnet. Whenever you kind of apply the current to this, how does this starts to behave? This behaves like a bar magnet. Okay, behaves like a bar magnet. Okay, what kind of magnet? Bar magnet. Okay, whenever the solenoid acts like an electromagnet, it behaves like a bar magnet. Got it? So it behaves like a bar magnet. Let me just highlight this part. Next, the magnetic field lines are uniform inside the electromagnet. Did you see? Someone kind of asked me a question. How will be the magnetic field lines? Inside it will be uniform. First thing, it is uniform and it should not intersect. Then what should happen? It should be parallel, right? If it should not intersect and it should be uniform, it has to be parallel. Remember, someone asked me the question, so remember this point. Okay. Now this acts like a big bar magnet. Okay. Bar magnet. What's this? Solenoid. Okay. A solenoid acts like a bar magnet. This is bar magnet. Clear? I hope this is clear, my dear students. Going to the next part. Okay. Hi Vanshi, welcome to the class. Hello there. Okay. Now guys, how can you increase the strength of electromagnet? You got to know electromagnet. Solenoid is a kind of electromagnet. Why? Because the current is flowing through the solenoid, and whenever the current flows through the solenoid, it's like kind of behaves like an electromagnet. Okay. Strength of an electromagnet, strength of a solenoid. How can you reduce or increase or decrease the strength of a solenoid? Okay. Uniform means, Prabhakar, uniform means it will be having equidistance between them. Okay. See, if you've got like 3 fingers having gap, the gap between them is same, we say that's kind of uniform. Got it? Yes, in an order. Okay, which is look alike. The distance between each field lines will be same. Okay, I hope that's clear. Strength of an electromagnet, that's solenoid. How can you increase or how can you decrease? Okay, now if you want to increase the number of if you increase the number of loops of a solenoid, so what happens? There will be lots of north poles, south poles which are merged together, so you can have more what? Magnetic field. Okay, or increase the strength of current. If more current flows, well, the magnetic field strength also increases, right? You can also say that. or increasing the strength of the rod. See, what is this is that, imagine you are keeping a rod inside of it. This is made up of a magnetic material like iron, okay? So this core, because of the influence of magnetic field, try to behave like a big magnet itself, okay? Yes, so in the great. So the three ways we can kind of increase the strength of electromagnet: increase the number of loops, more current, or increase the current itself, okay? More loops, more strength, okay? Increase the current itself. See, you are kind of increasing the current. Instead of a cell, you are adding a battery, okay? Increasing the strength of current, or increasing the core itself, okay? By number of loops, number of curves, whatever you said, okay? Curls, right? So this is how you are kind of increase or reduce the strength of an electromagnet. Is it done? Is it clear, my dear students? I hope this is clear. If a question comes from magnetic effect of electric current, let it be on solenoid, properties of magnetic field lines, or let it be clockwise rule, anything, Oersted experiment, I don't think you will be feeling lots of discouraged, right? You will be super confident because you have attended this class. Of course, magnetic effect of electric current, you've got 95% of whatever they ask you in the exam, okay? Now you've got a poll. You've got a poll, 60 seconds, and the poll starts, okay? The poll has started. Just go ahead and give me your answer. The strength of an electromagnet can be increased by, this is not decreased, okay? Increased by, okay? Prabhakar, okay, I'm really flattered by your comments, man. Thank you, thanks a lot for attending as well, okay? A, B, C, or D. How are you going to increase the strength of the electromagnet? Quick. Give me your answers. And the timer is running. Whenever you give your answers, your names will be shown in the leaderboard, which you can flaunt in your social circle, okay? The time is running. You've got like 10 more seconds. Quickly, guys. Quick. Type A, B, C, or D. Okay. Yeah. So I'm gonna kind of stop the poll. How? Increasing the current to the coil. We just saw, right? Decreasing the current? No, of course. This does not help. What about this? Decreasing the number of... No, we have to increase using a weaker core magnet. Nah, not right. So only right answer what we have over here is option C. Option C is the right answer. Let's see how many of you have given the right answer. 100% of you have given the right answer. Manoj is asking the leaderboard. Here is the leaderboard. And guess what, Manoj? You are in the top 5. Okay, hats off to you. Okay, let's see the entire leaderboard for now. Okay, shall we see the entire leaderboard? Here, out of all the polls, okay, after all the polls, Indu Anup is at top, Siba top 2, Bhargavi 3, and we've got many others in the session. Got it? Great. Nice. I really enjoyed having an interaction with you. Going to the next part, my dear kids. Okay. Next part. See, you have got this thing called as Fleming's left hand rule. What's this? Why do we even kind of want to learn this? Well, Fleming's left hand rule is used to help you understand. Whenever you have a magnetic field, okay? Imagine you have a magnetic field and you are going to keep another magnet to that. What happens? The magnet is either pushed or pulled. What kind of force is acting on that? The similar scenario will also happen, okay? Now, see, I'm going to explain why Fleming's left hand rule is required, okay? If, imagine you have magnetic field lines, uniform, okay? What does uniform means? It will be kind of having uniform distance, okay? This is magnetic field lines. I'm going to kind of copy it if it's possible, okay? Do we have a copy option over here? Copy. Okay, I want one more. Over here. So I'll copy one more. This is how, imagine you have magnetic field lines, okay? What do we have here? We have magnetic field lines over here and they are uniform. Why do we say they are uniform? They are uniform because they have got equal space behind it, right, my dear students? Now, this is a magnetic field, okay? Now, this is a magnetic field. Now, if you keep a current carrying conductor, okay? So, what does this say, my dear students? This is what? This is a magnetic field, okay? This is a magnetic field, okay, field. Now, if you keep a current carrying conductor, imagine you are going to keep a current carrying conductor in this field, okay. There is a straight current carrying conductor kept in this field, okay. There is a straight current carrying conductor kept. What is the direction of flow of current? Well, I'm going to say the direction of flow of current is this. Now, in this case, what happens? There is already a magnetic field and there is one more magnetic field because of current carrying conductor. What's this? This is a current carrying conductor, okay? Current carrying conductor, okay? Now, what is the force experienced by this straight current carrying conductor in what direction, okay? So it, of course, current carrying conductor has its own magnetic field, right? Its own magnetic field, right? Magnetic field. Now, of course, it has to be either attracting or it has to be repelling. If it attracts, or what kind of force is acting? Well, to know that, you would require Fleming's left hand rule, and force over here is given by F is equal to BIL sine theta, okay. Now, if this is the angle it is making, the amount of magnetic field, length of a conductor, and the current, and the angle between these two, okay. Now, in this case, what shall we use? We will be using Fleming's left hand rule. What does Fleming's left hand rule says? You have to use your left hand and stretch 3 fingers which are perpendicular to each other, okay. So first finger is thumb, okay, perpendicular to thumb, 4 finger, you can see 90 degrees, and middle finger is perpendicular to 4 finger, 90 degrees. So all these 3 are perpendicular to each other. Now what happens in this case? In this case, when you align your 4 finger in the direction of magnetic field and the middle finger in the direction of flow of current, thumb will be automatically giving you the force experienced by a straight current carrying conductor kept inside the magnetic field. I hope you all understood this, right? Is it clear? So it says that, what does Fleming's left hand rule says? The Fleming's left hand rule says that, shall I write Fleming's left hand rule for you, my dear students? It says that when you stretch 3 fingers of your left hand, okay, Fleming's left hand rule. Fleming's, okay, left hand rule, okay. Stretch 3 fingers, first 3 fingers of, first 3 fingers of your what hand? Left hand. And what are your first 3 fingers of your left hand? Those are perpendicular to each other. This is 90 degree. What does this say? These are perpendicular. All 3 fingers should be perpendicular to each other. Very good. Prabhakar, father, mother, child, I will help you, okay? Perpendicular to each other, okay? Perpendicular to each other. What happens? And if 4 finger, okay, 4 finger is aligned in the direction of magnetic field, and middle finger in the direction of flow of current. What is the direction of middle finger? Middle finger should be aligned, okay. 4 finger is done, middle finger, okay, middle finger in the direction of flow of current. Then what does the Fleming's left hand rule says? Automatically the thumb will be giving the direction of force acted on a straight current carrying conductor kept on a uniform magnetic field. Then what happens, my dear students? Then this is if you keep it, then what happens? Then thumb finger gives the direction, okay, direction of force where? On a current carrying conductor, on current carrying conductor kept in uniform magnetic field, okay. So how do you remember? Sir, how shall I remember? Okay, see, now thumb is F, okay, thumb says F, okay, it is the force, okay. Thumb is kind of telling you the force. This is thumb, okay, thumb. Now what is magnetic field? F, 4 finger, right? So F, magnetic field is given by 4 finger. This is 4 finger, and current is given by the middle finger, okay, middle finger. Or you can remember, father, mother, and child. It's like father is like force, mother is magnetic field, I is current, okay. Thumb is like F, father. Father is what is going to be discovered later, okay. It's kind of like that. you know where mother and child are with the help of, if you ask them, they'll be giving you the direction of father, right? So where he or she is there in the park. So this is how it is, okay? You can either remember FBI or you can just remember father, mother and child, okay? Instead of B, you have magnetic field, okay? Clear? Right, okay? So it's like force, you know, it's not force finger, this is forefinger, okay? This is like what finger? It's forefinger, the first finger, the one which you used to point it. I hope this is clear. Yes or no, my dear student? Is it clear? Okay, thanks a lot, Kriti. Kriti says it's clear. And if you have any doubts, you can easily ask me. Now, well, that's all for the magnetic effect of electric current, okay? We have learnt a lot and covered most of the part of magnetic effect of electric current. Now, magnetic effect is done. 3 more chapters are left. Which do you want me to start? Electricity, or you want me to start light and human eye? Which one? Okay, shall I just give you a poll? Overloading Manoj. Yes, in electricity, we are going to kind of start about all those things, galvanometer, overloading, everything. Shall we start electricity or what? Okay, shall I give you a poll which has to be started? I'll give you a poll, okay? I'll give you a poll, okay? A, if you want light, okay, vote A. And if you want human eye, okay, vote B. Option C, if you want electricity, okay, electricity, vote C. And D is done. D, magnetic effect, it's done, okay? You've got 60 seconds. Whatever vote will be coming, I'll be taking that chapter next. Quick, quick, quick. A, B, C or D. You decide, okay? It's like, it's in your hands. A, B, C or D. You decide and I'll be kind of helping you out, okay? Quick, quick, quick. AC, DC. A, C, A or C, D or C, or you're talking about current, A and C. Quick, timing's running up. Whichever chapter you want, you decide. Whichever chapter you want, you decide, okay? Guys, time is ticking. Quick, it's in your hands. Whatever you want, that is what I'm going to kind of take today. Quick kids, quick. All right, is it done? Is it done? Okay, it's not automatic current, it's alternating current. Okay, we'll talk about that. I kind of want to discuss C. Let's see how many requires what. 85% want electricity. I know you are been waiting for that. So without any further ado, let's directly jump into the electricity concept, okay? And then I'll go with light and human and colorful world in the same order, however it is, okay? Overloading, everything is there. You just have to wait, okay? Wait and everything will be here. Done. Guys, are you ready for electricity? Electricity is what chapter? Chapter 2, right? Electricity in your CBSE is chapter 2, okay? Everything will be discussed. Domestic circuit, earth wire, fuse, everything in detail. This is for your boards. For your boards, we are here to help you. And do you think we are going to miss any part? Definitely not. Nothing will be missed, okay? This is chapter 3 in your CBSE, right? Chapter 3 in your CBSE. Okay, now let's get started. Now, what is the scenario? Can you imagine yourself? Let's quite relax for a while. Of course, it's been like more than 1 hour, 10 minutes and you are watching with such a high energy. Let's relax. Now, what is the scenario? Do you get to see any power over here? Okay, no, right? We cannot kind of expect this kind of stuff. This is how we live, right? So with lots of electricity, all the gadgets and all, so we have to talk and learn about electricity, okay? Yeah, my dear student, numericals, you can expect numericals in first and third chapter. And do you think I'm going to miss numericals? Never, okay? No need break, sir. We are full ready. Yeah, my dear students, break will not be given so soon, okay? Right. Lots of numericals are there. Wait, your polls, your leaderboard will be shown here. But let's talk about some basics here, okay? Yeah. Now, talking about the fundamental property of matter, that's atom. Inside atom, you'll be having protons, neutrons, and electrons, right? So, electrons are over here. in the nucleus at the center will be having protons and neutrons. But remember, electric current is only because of electrons, flow of electrons. Okay, so what's electricity? Electricity is kind of just saying in what direction the electrons flow. It's like flow of electrons. Flow of electrons is what we are going to call it as electricity. Okay, simple as that. Okay, whenever they ask you what's electricity, you will be saying that's flow of current. Okay, flow of any electrons. Now, hi there, Lakshman Singh. Hi there, how are you? Okay, now coming back to electric current. Okay, let's understand what electric current is. Now, my dear students, imagine you are in a water stream. Okay, you are inside a river and there is a loud speaker saying that do not go further, the water current is so high. What does that mean? So the water which is flowing is super strong, it is going to kind of pull you, so do not go there. So that's what is what the tell me, that's what is what the current is, water current. Similarly, the wind current will be more on the top. That's what is electric current is also. Electric current is just flow of electrons. Okay. How to answer poll? Muhammad says, see, poll does not pop up. When the timer starts, you have to say A, B, C or D for multiple choice in the live chat and your answer will be recorded. Okay. So what's electric current? If they ask you a question, electric current is flow of electrons. Okay. No link is there, Muhammad. Okay. Electric current. Electric current is what? Current is flow of electrons. Okay, flow of electrons. Sir, is it right? But there is something called as conventional flow of electricity. What's that? What's the conventional direction of flow of current? Well, I will help you. In the olden days, scientists had thought the electrons are not the cause of current, but instead protons. So protons is positive, electrons is negative. If electron goes like this, proton goes in the opposite direction, right? That's what it is. Okay. Now, if they ask you a question, well, this might also be an important question. See, an important question is about to come from this chapter. What is the direction of flow of conventional current? Okay, conventional flow of electric current. Conventional electric, okay, direction of electric current. Okay, what is the direction of flow of conventional electric current? I said yes. In the olden days, they believed that electric current is due to because of protons, and if electrons flow like this, protons flow in the opposite direction. So it's as simple. A conventional electric current flows in the opposite direction to the flow of electrons. Conventional means olden days, Prabhakar. Understood? It's like old. It came from very long. Conventionally it came. Okay. Conventional means I just told you. Okay. So what shall we write? So the conventional electric current, the direction is, okay, direction. The direction of conventional flow of current, direction is opposite to what? Opposite to the flow of electrons. The flow of electrons. Okay, electrons. This is what, my dear student, is the direction of flow of conventional current. Okay. Increase the sound. Well, sound is at max, my dear students. Can someone tell me whether the sound is audible or not? Everyone just say in the comments whether it's audible or not. Okay. Now, I hope this is clear, everyone. Is it clear, right? So, the conventional direction of electric current is opposite to the direction of flow of electrons. How? This is like 2 marks question, okay? Or you might also expect this for 1 mark or 2 marks, okay? So remember to do this, okay? Great, thank you for the confirmation, Manoj. Now, see, we just talked about protons and electrons. Don't you want to kind of know about the charges? Okay, Joy, thanks for the confirmation, okay? Yeah. Now, talking about the properties of charges, let it be proton or electron. You just got to know about the current. Current is because of flow of electrons. But what will be the properties of that? How many marks you might expect this for? 2 marks or It can also be for 3 marks, because for 3 marks you have to write all the points without missing anything. Got it? Is it clear? What's the duration of class? It goes for somewhere around 3 hours, my dear students, 3 to 3.5 hours, not more than that, because comprehensively we have to revise each and everything, so we need some time. Okay, now talking about the first thing, my dear students, protons, okay, protons have what charge? Positive charge. It has got positive charge, and electrons have got negative charge. Is it clear? This is the first point you might kind of write when they ask you to talk about the properties of electric charges. And like charges attract and like charges repel, just like how I said in magnetism. Remember, if you have north poles, two north poles come aside, two south poles repel, one north, one south, they attract, right? Similarly here, like poles attract, okay? Like charges attract. It's not poles here, it's charges. Like charges attract, okay? Charges attract, okay? Attract. And what happens to unlike charges? They repel, okay? Like charges repel, sorry, just like in the magnets, okay? Like charges repel, and unlike charges attract, okay? Unlike charges attract. Clear? So do not make the mistake. Just like in the magnet, like poles repel, right? Here also we have that, okay? Now that means if you have two positive, okay, two positive charges, they repel. Two negative, they repel. One positive and one negative charge, they kind of attract. Got it? I hope this is clear. Now talking about next part, the charges are conserved. What does that mean? That means to say that the number of charges is kind of same in the entire universe. Law of conservation of energy, just like how you cannot create or destroy energy, you cannot create or destroy the existing electrons or the charges, okay? So charges are conserved, okay? Charges are conserved, okay? Next is the important point. Charges are quantized. What does that mean? That means the charges, electrons will be like 1, 2, 3, 4, 5, like that. You cannot expect half electron or 3/4 electron. Never. How can you expect that? That never happens. Okay. Okay, Preetham, what's your doubt? Just tell me a doubt. I'll be able to answer that. Okay. Charges are quantized. Okay. Charges are quantized. Okay. Okay, charges are quantized. That means electrons can be, you know, number of electrons can be 1, 2, 3 and so on, and not 2/2 or 3.5 and all. Okay, conserved means you cannot create or destroy electrons. That's what it means. Okay, next, last thing, that is charge on one electron. Okay, charge on one electron is minus 1.6 into 10 raised to the power of minus 19 coulomb. I hope you understood. So these are all the different properties of charges. I hope you understand. Okay. Now talking about the concept, charges are conserved. Okay. On that I want to discuss one point. Okay. Charges are conserved. Okay. Charges are conserved. What does that mean? Okay, conserved means the electrons can be in like 1, 2, 3, 4, like that. It cannot be 2.5, 3, 1/4, like that. It never happens. Okay, for example, we have Q is equal to Ne. Okay, where Q is total charge, N is number of electrons, E is charge on one electron. Okay, now if you have two electrons, okay, two electrons, the charges would be how much? Charges Q is equal to N is how much? N is number of electrons, 2 electrons, and E is what? Charge on 1 electron, my dear student. That is 1.6 into 10 power minus 19, right? So 1.6 into 10 power minus 19. Okay, how much does that get? So 2 into 1.6, my dear students, tell me. 2 into 1.6 will be 3.2 into 10 power minus 19 coulomb. Is it correct, sir? Yes, it's absolutely correct. But, okay, but the charge, okay, I'm going to tell you one charge, okay. It's like if I say charge of 2.4 into 10 power minus 19 does not exist, okay, does not exist. Why does not exist? See, this is also such an important question in your board, okay. In your board they will ask a question like, if 2.4 into 10 power 19 charge exists or not, yes or no, okay. Hi Sanmitra, welcome to the class. Hello Aditya, Sanmitra, welcome to the class. How are you doing? We've got Preetham. Is it possible that an atom can be stable without a, okay guys, physics is happening here, okay. Now let's focus over here. The charge of 2.4 into 10 power 9 minus 19, is it possible or not? Let's see. See here, we know Q is equal to NE, right? So what's the Q given? Q is given to be 2.4 into 10 power minus 19 is equal to number of electrons. Let's find it out. And what's the charge on one electron? It's 1.6 into 10 power minus 19. So if we find number of electrons, we will be getting 2.4 divided by 1.6 into 10 power minus 19 divided by 10 power minus 19. This gets cancelled. How much do we get? Can you tell me? 2.4 divided by 1.6. 2.4 divided by 1.6. 1.5. Do you think 1.5 electron exist? Do you think this exists? No, right? Guys, this is an important board question, okay? This might come for your boards. This is board question. What does they say? If a 2.4 into 10 power 19 coulomb of charge exists or not? How do you say? Okay. Sanmitra, Joule's law of heating will be there soon. I'm going to explain. Just wait, okay, my dear student? Alright, Joule's law of heating will be explained. See, this is how we say charges are quantized, okay? If we say charges are what? Charges are quantized, okay? Charges are quantized. That means charges will be like 1, 2, 3, 4. Electrons will be of 1, 2, 3, 4, okay? Now, this is what we say, okay? If 2 electrons are there, it gives this much charge. Well, this is fine. But the charge of 2.4 does not exist. Why? Because of electron. That's because if you try to find the number of electrons, you're getting 1.5. This is definitely not possible, right? So this is why we say charges are quantized. Is it clear? Give me a thumbs up if it's clear. You can go ahead and give me a thumbs up if that's clear, okay? Siva says, current flows from positive to negative, then does conventional electricity flow from negative to positive? Well, the other way around. Actually, current flows from negative to positive. Conventional current flows from positive to negative, okay? Ohm's law, Aditya, yeah, we are going to discuss Ohm's law. Hindu Anup, thanks for confirming. Thanks for the thumbs up, okay? Now, going to the next part. See, there is a pole for you, okay, and the timer starts for the pole. A body has some charge Q on it as shown. What are the possible values of Q it can have? What are the possible values of Q that it can have? You should be telling. How to do it? A, B, C or D, let's see. See, divide everything, okay? Divide by 1.6 into 10 power minus 19. If you get a natural number, okay? If you get a natural number, positive integers, 1, 2, 3 and all, well, that charge exists. After dividing by charge on 1 electron, if you get a decimal, that means it does not exist, okay? So then how 3.2 exists? That's a good question. That is charge, okay? See, 3.2 divided by 1.6 into 10 power 19. If you do this into 10 power minus 19, how much you would get? 3.2. 3.2 divided by 1.6. 3.2 divided by 1.6, you'll be getting 2, right? See, 2 is possible. I said no, 2 is possible. This is how you have to do, my dear student. Is it option C? Let's see. So, if you do 4.8 into 10 power minus 19 divided by 1.6 into 10 power minus 19. Why you have to divide by this? Because this is charge on, because this is charge on one electron. This is charge on one electron. That's why you have to divide. So that gives you total number of electrons, right? What formula are we using here, my dear students? Q is equal to NE. This is the formula what we are using. Shall we do this? How much you will get? 4.8 divided by 1.6 will be giving you 3, yeah, right? So this is 3, right? Yes, 3 electrons exist. If you do all these things, I know you won't be getting the right answer. Option C is the right answer. Let's see how many of you. 66% of you have given the right answer. Great, my dear students. Hats off to you. Okay, clear? Let's see who all have given. Indu and Prabhakar has given the right answer. Remember, calculators are not allowed. So you have to kind of have enough confidence to do it alone without using the calculator. Is it clear? Is it clear, my dear students? Shall we go to the next slide? Yes or no? If you say it's clear, we will be going to the next slide. Okay. Now, let's move to the next slide. Calculate the number of electrons because of 1 coulomb of charge. So they are giving you Q is equal to 1 coulomb on charge on 1 electron. You know 1.6 into 10 power minus 19 coulomb. So number of electrons we don't know, right? Shall we do it? Yes, sir. We shall do it. Okay. Now, how do you do it? So Q is equal to NE. Q is equal to NE. Number of coulomb 1. Number of electrons has to be found out. Charge on 1 electron. 1.6 into 10 power minus 19. Now, N would be what? N is 1 divided by 1.6 into 10 power minus 19. Now, if you do this, 1 divided by 1.6 is how much? 1 divided by 1.6, 0.625. N is equal to 0.625 into 10 power minus 19 goes to the numerator, becomes plus 19. Sir, is it possible? Yes or no? Tell me. Is it possible? Yes or no? You might say, sir, this is a decimal, it's not possible. How would you say, sir, this is possible? Huh? Well, if you see that in front of that, how many zeros you have? How many zeros you have? Okay, you have got N is equal to 6, 2, 5 into 3 zeros you can remove, right? 10 power 18, 17, 16, 10 power 16 electrons. If you see this, don't you think this is possible? See, this is what kind of number is this? It's a natural number. Don't you think this is possible, my dear students? Yes or no? Right? Do not look into the part. Do not look into the part which says only decimal. Look into the part which also says which is possible. Okay. So remember, 0.625 is not a decimal. It is in fact an integer. Okay. Great, Prabhakar. 6.25 into 10 power 18 electrons. Yeah, you can also do that. Right. Shall we go to the next part? I hope this is clear. This kind of questions will be coming in your exam. Okay. Now, what is ammeter and how is it connected in the circuit? Well, to know about this, you should know how current works. Okay. Well, to talk about ammeter, ammeter is a device. Ammeter is a device used to measure current in the circuit. Okay, to measure current in the circuit. Okay, current through the circuit, through the circuit. Okay, so this is what is ammeter, and how is it connected you will know soon. Okay, so yes, very good. It is used to measure the current in the circuit. Okay, now you know what the thing is, how is it connected? See, the current flows through the circuit. The current flows, the current kind of divides only when it has got two parts. Okay, to know this, you should know current flows. Okay, flows through. Okay, through anything. Okay, current kind of flows. How? Current kind of flows through anything, right? So if you want to measure the current, you have to connect the ammeter in such a way that the current passes through the ammeter, right? The current flows through. So to measure the current, measure the current, okay, it has to pass through the ammeter, okay? It has to be connected in series, okay? What is series? Well, I'm going to explain what series is. Imagine you have a battery over here, okay? You have a battery, and what is happening? You have some resistor, and in this resistor, how much current is flowing? You should know, okay? So how much current is flowing through this resistor, you should know. So in such cases, what do? Is we kind of connect this in series, okay? The same current has to flow through this, and the current also flow through this. So the ammeter is connected in series. Got it? Is it clear, my dear students? So ammeter is connected in series in the circuit, okay? Current can flow through the conductor and semiconductor. Yeah, right. Let's look about it, okay? Now we just saw electric current, right? How do you define electric current? See, current you just saw, but how do you define electric current? Okay, I is equal to electric current. Okay, electric current. Electric current is given by rate of flow of charges. Okay, it's defined as rate of flow. Okay, rate of flow of charges. Rate of flow of charges is what is our electric current. Well, what's the formula for it? I is equal to Q by T. See, we just saw what electric current is, but how does this electric current is defined? Is rate of flow of charges. SI unit of charges is coulomb, right? Coulomb, and SI unit of time is second. Okay, second. So what would be the SI unit of electric current? It will be either coulomb per second, or you can easily say, or SI unit will be ampere. What is SI unit? SI unit of electric current is, my dear student, it is ampere. Clear? So there will be a question, what is the SI unit of electric current? Electric current is ampere or coulomb per second. What is electric current? Electric current is flow of charges. Okay, rate of flow of charges is what we're going to call it as electric current. Clear? Is it clear, my dear students? Okay, sir, do you think electrons will be just kind of going? Do you think something else should be there? Well, the electrons will not move on its own. There has to be someone who pushes the electron so that the electron actually moves and creates an electric field. So this kind of pushing force, okay, the pushing force, okay, which causes electrons to flow, okay, which causes electrons to flow. What do we call it as? Flow is called as voltage or called as potential difference. Okay, it's voltage. What is voltage? It is kind of the push required to push the electrons so that it flows. See here, if you have electrons is like me and you. It's like follows inertia. So if you are watching TV with a big bucket of popcorn, even though it's time for study, you wouldn't get up, right? Just like me, Gen Zs, right? So what happens? Your mom has to push you. Hey, get up, go and study, you've got exam, right? Similarly, electrons will be there wherever it is. It does not kind of change its position. Someone has to push it, right? So such kind of pushing force is what we are going to call it as voltage, okay? So it's like to define it. So this is for you to understand. Do not write this right in exam, okay? To understand, I just gave this example. It's like the work done in moving a unit positive charge between any 2 points is called as potential difference. Got it? So how do you define voltage, sir? My dear students, here it is the voltage, okay? Voltage is given by, okay? Voltage is work done in moving charges, okay? In moving charges between 2 points of electric field. So my dear students, what's going to happen? So work done is given by joules, right? SI unit joules divided by charges, it is coulomb. It is coulomb. So SI unit will be joules per coulomb, or you can write in one easy way. SI unit can also be written as volts. SI unit is also written as what? Volts. Is it clear? What is the SI unit of voltage? It's either joules per coulomb according to definition, or it is volts. I hope this is clear. Aditya Dubey, doubt. What's the doubt? Please tell me your doubt in the chat section. Okay. What is the 2 points infinity? Please explain. See, my dear student, it's like imagine you have, it's just for you to understand. It should not be infinity between 2 points if you want to bring charge, okay? Or you can write the force which causes the electrons to flow, okay? That is what is voltage, okay? What is coulomb? Okay, Aditya Dubey, coulomb. Let's see what is coulomb, okay? I'll tell you what coulomb is, okay? Coulomb, here C is coulomb. C is coulomb. That means that is a measure of charge. It's a unit required to measure of charge. Measure of charges, okay? Charges, where you know Q is equal to NE and Q is given in coulomb. This is the SI unit. Coulomb is what? It is SI unit of charges. Is it clear, Aditya? Everything is required, okay? Okay, shall we just go ahead and proceed with our understanding of voltage? And one more thing, that's resistance, which I will be talking about soon. So voltage is work done to bring charges from two different points, work done on charges, joules. SI unit of charges is coulomb. So what can we say, my dear students? Joules per coulomb is our voltage. SI unit of voltage is volts. Clear? Is it clear? Okay. Now, talking about something very important, okay? Resistance. Three things are very important to understand Ohm's law. Voltage is done, current is done. The one thing that you have to know is regarding resistance. What resistance is and how does this act is very important, super important, okay? Now, do you think life is easy? Life is not easy, sir. I have to study chemistry, bio, physics, languages, social, there is computer science, lots and lots more, right? Life is not easy, right? So I said voltage is what? Voltage is pushing force, right? You can see here, this voltage is kind of pushing this voltage, okay? This voltage is pushing electron, right? What is this voltage is doing? This voltage is kind of pushing electron. This is electron being pushed, pushing electron. Now, what is this resistor doing? This resistor, do you think that is leaving it? No way. The resistor is like, no man, I'm not gonna let you do your work. Voltage, I'm kind of opposition for you, is what the resistance is, okay? So this resistance, this is over here, is resistance, okay? Resistance is opposition for flow of electrons, okay? Or you can say it is opposition for flow of what? Opposition to the flow of electrons. Flow of electrons is what we are going to call it as resistance, okay? Life is not so easy. It's like a trouble causer for voltage, okay? Even though the voltage is pushing, the current is not kind of moving. So this is how you understand resistance, okay? Now, so once you know this, it's easier for us to understand something called as Ohm's law, right? So once you know this, it's time for us to understand Ohm's law. What does Ohm's law say? It's very simple. Ohm's law kind of talks about the voltage, resistance, and the current itself, okay? What does Ohm's law talks about? Ohm's law talks about voltage, current, and resistance, okay? Sir, just now you told about three things. Voltage, you said that's the pushing force which is pushing the electrons. You said about current, that's the flow of electricity. This is the resistance. So is there a law which says that? Definitely. Writing it in a proper format will be giving you the Ohm's law, okay? So what does Ohm's law states? If they ask you in the exam, the current flowing in the circuit, okay? The current in the circuit, okay? The current in the circuit. How much current is flowing depends upon how much push you are doing, right? See, if you are applying more push, if you are applying more force, more electrons can go. But on top of that, we do have resistance. So how does that goes? The current in the circuit is directly proportional to applied voltage, right? Applied voltage, okay? applied voltage given. Is it that? Is it the Ohm's law? No, we have when, okay, when uh, uh, physical parameters, temperature and physical parameters are kept constant. Temperature and other physical parameters are kept constant. Okay, parameters are kept constant. Remember, kept constant. What is this? This is our Ohm's law, my dear students. Okay, so for how many marks they will ask you? With graph, 2 marks. Okay, without graph, 1 mark. Ohm's law. Okay, this is what Ohm's law says. Now shall we visualize this? How to visualize this, sir? Now it says that how much current is flowing. Okay, how much current is flowing? V is applied to. The amount of current flowing is directly proportional to what? Is directly proportional to the applied voltage, provided the one thing that is kept constant, that is our resistance. Okay, derivation, yeah, kind of, it will be asked, I'll tell you. So we can write V is equal to I times R, where V is the voltage, R is the resistance, I is the current. Okay, so if I have the space, I'm going to write. So SI unit of resistance, SI unit of resistance, shall we write it? So SI unit of resistance is ohms. Okay, SI unit of resistance is ohms, given by this symbol. And if you rearrange it, you will be getting R is equal to V divided by I. I hope this is clear. This is how Ohm's law will be asked. A graph regarding Ohm's law? Yes, definitely. Why not? See, we have Y in y-axis we've got voltage, and in x-axis we've got current. In this case, how does the Ohm's law work? Well, the slope is the steepness, right? So what does slope says, my dear students? A slope is change in y-axis, y2 minus y1 divided by x2 minus x1. So what do we have in y-axis? In y-axis we have voltage, right? So voltage divided by x-axis, you've got current. So V by I is what? R. R is resistance, just like how we studied before. Got it? So this is regarding Ohm's law. Okay, now sir, do they ask us some questions like how do you try to draw some of the different electrical symbols? Yes, they might also ask you, right? Yeah, Prabhakar VI graph, whatever you said is right. Okay, so now talking about different electrical symbols, are you all ready to talk about different electrical symbols? Let's get started. A cell is represented like this, with positive terminal to be bigger than the negative terminal. What is a battery? Combination of cells. If you have one cell and you have another cell, okay, another cell, and you have another cell, it's like combination of different batteries, different cells, my dear students. That what is battery. Okay, plus minus, this is how it will be. Okay, so this is what is electrical symbols. Now talking about one more thing, that's plug or switch. How is it shown? This is how it is shown. This is like switch close. If the current flows like this, there is no path for the current to go, right? But plug close or key close, it's like you are going to show a contact, electrical contact. So when the current goes, a metal, it flows through this. Okay, clear? Derivation, well, derivation for series or parallel, it might be there for resistors, which I will tell soon, but you have to wait and watch. Okay, study. Okay, Aditya. Yes, resistance ka derivation will be there for series or parallel. I'm going to tell you pretty soon. Okay, now how does resistance look like? Resistance is the opposition for flow of electrons. This is how it looks like. Well, rheostat, it is a variable resistor where you can just change the amount of resistance. Got it? You can kind of change the amount of resistance. A resistor with this is what you're gonna get it. Okay, next, electric bulb. Okay, electric bulb is represented like this. Okay, now talking about one last thing, a wire joint. Okay, if you kind of have a wire which is joint, okay, this is one wire and this is one wire, it is joining over there. But if you have two different wires which are not joining, it goes like this, which is going on top of that. Ammeter, which measures the current, is given by A. Voltmeter, which measures the voltage, is given by V. Clear? I hope this is clear. All right. Uh, yeah, my dear students, everything will be discussed, okay? Prabhakar, don't worry, series and combination, I'm going to teach you in such an easy way. By the end of the session, you will be like, sir, well done, sir. I'm so happy with that, you will say, okay? Now, see, we just understood how a ammeter has to be connected, right? How an ammeter has to be connected? Ammeter has to be connected in series because current flows through it. How much current is there? That current has to flow through the ammeter. And remember one thing, how much should be the resistance of ammeter? Resistance of ammeter should be less, right? Resistance of ammeter should be less, okay? Ammeter should be less, okay? Should be less. This is about ammeter. Talking about voltmeter, my dear students, how voltmeter should be connected is very simple. Voltmeter is a thing which measures the voltage, okay? How much voltage is there between 2 points, okay? The voltage will be kind of between 2 points, not through the circuit, okay? Voltmeter measures the voltage and it is connected parallelly, okay? Let me write it on the screen, okay? Voltmeter measures, okay, measures voltage, okay, voltage across 2 points, okay, across 2 points. And how this voltmeter has to be connected? Voltmeter has to be connected not in series, but it has to be connected in parallel. I hope you got it right, my dear students, because the voltage is between 2 points, right? So it's kind of voltage is measured in parallel. So voltmeter has to be connected in parallel, okay? Voltmeter is connected in parallel to the circuit, okay? Parallel to the circuit, because the voltage kind of doesn't divide across any parallel. So voltage will be kind of same. Okay, is it clear? Ohm's law, current, voltage, SI units of it, charges, ammeter, voltmeter, how is it connected? Different symbols, right? Now it's time for us to talk about, yes, resistors, okay? Now see here, resistor you said, sir, but what are the factors that kind of depends upon that the resistor depends upon? There are 3 factors, okay? See, the R is resistor, I said, right? R is equal to rho L by A, okay? Imagine you have a big road, okay? And in the road you've got obstacles. These are the small obstacles what you have in the entire road, okay? If you have obstacles in the road, what are you going to do? You have to kind of cross the obstacles and go, right? As the length is more obstacles, right? If the length is more, the electron has to collide with more obstacles, so resistance will be more. But imagine if the area of cross section is big, the number of obstacles is same, but the road is bigger. In that case, what happens? Without hitting to the obstacle, you can kind of easily go in this path, right? See, if the area is kind of big, without colliding, you can easily go like this, right? So it is inversely proportional. If the road is bigger, resistance is lesser. If the length is bigger, resistance is more. So these are the factors that the resistance becomes, okay? Regarding this, I will tell now. Rho, okay, regarding this. See, the factors affecting resistance, I'll tell you, okay? Factors affecting resistance, okay? Factors affecting resistance. Affecting resistance. Resistance, okay? Now, see, I introduced the word rho. What does rho means? Yeah, of course, I got a question. Everyone are asking. I'll tell you, just wait and watch, okay? Well, R is equal to rho L by A, okay? Well, rho is, it's like how much resistance is there per meter. It is specified for all the metals, okay? Like metals, materials, okay? If you take copper, this much 1 meter of copper has got this much resistance. It's decided. You take a copper on Earth or you take copper on Moon, Mars, wherever you find it, the rho will be same. That means resistance per meter will be same. So that's what we say. Rho is resistivity, okay? Resistance per meter it would be same for all for different materials. Okay, so resistivity is represented by rho. SI unit is ohm meter. Okay, now talking about L length, as L is length. Okay, L is length. Well, if the length is more, resistance is more. Length is how? It is directly proportional, right? Directly proportional. Okay, this is directly proportional. What about A? A is area of cross section. That's the thickness, my dear students. Okay, what's A? A is area of cross section. Okay, area of cross section, that means thickness. Remember, it is a fancy word, area of cross section. Area of cross section itself means what? It is thickness. Clear? Is it clear, my dear students? Difference between resistor and resistance. Okay, resistor is a device, resistance is a property. A resistor has got this much resistance. Resistor is kind of, you know, the device itself. Okay, okay, area of cross section, or we can say what? This is thickness. This is thickness. I hope that you understood. Okay, how is thickness? Thickness is inversely proportional. Okay, inversely proportional. That means if you increase the area of cross section, resistance decreases. Okay, similarly, if you increase the length, okay, resistance increases. Clear? I hope this is clear. Okay, yeah, resistor is used to resist. Yeah, that's right. I hope it is clear. What is resistor, resistance? What are the factor resistance depends upon? Okay, now talking about that same thing. Okay, R is equal to rho L by A. Okay, so if you increase the length, the resistance increases. If you increase the area of cross section, the resistance decreases. R is equal to rho L by A. Talking about resistivity, it's like how it's going to allow the electrons. Good conductor has got low resistivity, bad conductor has got high resistivity. Got it? So no need to remember the resistivity of all the elements. It will be given in the elements. Shall we do a numerical? Are you all ready to do a numerical? Say yes or no, because this kind of numerical application, this will be asked in 5 marks. Remember, it will be asked in 5 marks. Okay, 5 marks. In 5 marks, you'll be having parts, right? One of the part for 3 marks they'll ask you. Okay, shall we do it? Okay, now see here, a wire of a given material having length. So there is a wire, it has got length L. Okay, and area of cross section A. It has got area of cross section A, and the resistance of 8 ohms. Okay, is it 8 ohms or 4 ohms? Shall we just, okay, it's 4. Can you see here? It's 4 and they have given you 8. It's not 8. It's kind of 4 ohms. Okay, it's how many ohms? 4 ohms have been given. Okay, shall I rewrite it? It is 4 ohms have been given. What should be the resistance of another wire of the same material having length L by 2? See, the length is half of the length, right? So this is L by 2. Okay, what's the length of the new wire? It is L by 2. Clear? Next, and the area of cross section 2A. Area of cross section is 2A. Now, with just seeing this, can you tell me whether the resistance will be more or less? By just seeing, you can see. See, according to this, we know R is equal to rho L by A. They are saying it is a same material. Same material means what is happening? Rho, resistance per meter will be same, right? Very good, Indu Anup. You said the right answer. Okay. Now, if the length is reduced, see, length is reduced. So if you kind of reduce the length, let's see what is happening, and I will solve and show it to you. Okay. So you know that R is equal to rho L by A, right? Right. So length is reduced. Okay. So if length is reduced, the resistance is also reduced. Area of cross section is increased. See, the area of cross section is made twice, right? So if the area of cross section is increased, the resistance is also reduced, because that's inversely proportional. Now what are we supposed to find? What should be the resistance of another wire? We are supposed to find the resistance of the second wire. I hope you are understanding, because we would be requiring this question 5 marks in board. Okay, they might ask you such kind of question. Let's try to solve this. We all know that R is given by R1. Let's find it. Let's call this R1. R1 is given to be 4 ohms. R2 is what we are supposed to find it. Let's do it. Okay, R1 is equal to rho. Okay, R1 is equal to rho L by A. Okay, because they're giving you rho is the resistivity, A is the area of cross section, and L is the length. Okay, sir, done. What about R2? R2. See, rho is same. Why rho is same? Because it is of the same material, right? So if it is of the same material, what happens? Same material, rho is same because it's of same material. For same material, resistance per meter would be same, my dear students. Such an important question. Focus, okay? R2 is equal to, what happened to the length? Length is L, becomes L by 2. They are saying, right? R into L by 2. L becomes L by 2. Okay. What about area of cross section? Twice 2A they are giving, right? So it is 2A. Shall we simplify? Yes. What are we supposed to find? We are supposed to find R2. Shall we do it? Yes, sir. So let's take R2 divided by R1. I'm taking the ratios, okay? What is R2? Rho L2, rho L by 2 divided by 2A. Okay, sir. What is R1? R1 is rho L by A. Rho L by A. Okay, sir. Rho gets cancelled. Okay. So R2 would be what? R2 would be kind of less than R1 because the resistance is less, right? Okay. Let's do it. So R2 by R1 is equal to L by 2 divided by 2A becomes L by 4A divided by L by A, right? Yes, sir. How to solve this kind of division, denominator of denominator goes to numerator, right? L by 4A into A by L, because it gets reciprocal. L gets cancelled, this gets cancelled. So R2 is equal to 1 by 4 times of R1. Can you see the resistance decreased, right? So the resistance is kind of reduced, my dear students. Okay, so 1 by 4 of R1. Very good. Wow, Kriti Agarwal has already said 1. Hats off, my dear student. Yes, 1 is the answer. Great, my dear students. Prabhakar says less. Yes, it is less. How much is less? Let's see. Finally, R2 is equal to R1 by 4. So R1 is how much? 4, right? 4 by 4 is equal to 1 ohm. It's not amp, 1 ohm. This is the important one. Okay, is it clear? I hope you understood. If this kind of numerical comes, I hope you will be doing no mistakes to be done, right? Will you do any mistakes? Yes or no? Mistakes will be done or not? No, right? No mistakes will be done. Right, I appreciate. See, simply we can say it will be reduced, but for how many times? This is how we should do, okay? Because verification it will be giving, okay? Clear? Now, going to the next part, okay? Variable resistor, that's rheostat, right? Rheostat is a variable resistor. How does that work? Okay, after this I'll be explaining series and parallel combination. Stay tuned, okay? Now, if you have a resistor like this, okay? If you have a resistor like this, okay, or I can just draw like this coil, okay? Coil will be giving you resistance, right? Now a slider will be there which can kind of move here and there, okay? So if the slider moves to this point, the length of the wire increases, right? So the resistance increases because R is equal to rho L by A, right? So remember, this is how rheostat, you can move it to adjust the resistance so the bulb can grow brighter or lower without changing voltage source. Yeah, we are going to talk about it. Okay? I hope you know about the rheostat. Now, here you have got a pole. Shall I start a pole? Pole of 120 seconds has started. What's the question? A copper wire has a diameter. They are giving you a copper wire, and the copper wire has a diameter of how much? 0.5 mm. And the resistivity of this much ohm meter. How much the wire would be required to make a 20 ohm coil? Okay, they're talking about the length of a coil. Okay, so I hope you will be able to do it. See, they're telling you need a resistance of 20 ohms, okay, and rho resistivity is given to be 1.6 into 10 raised to the power of minus 6 ohm meter. Well, this is in SI unit, okay. Now diameter is given, diameter is 0.5 millimeter. Millimeter can be written as 10 power 3 meters, right? It can be written as into 10 power minus 3 meters, right? Now how to find it? Okay, quick guys, time is running up. This kind of question, easy, 3 marks. Easy, 3 marks question. So remember how to do it. Okay, now you know that R is equal to rho L by A, right? So rho is given, L is given, R is, L has to be found out. Rho is given, R is given. What about A? A is pi R square, right? A is pi R square. So how do you do it? Guys, the poll is running. How do you do it? Okay, I'll be doing it over here. Okay, so area is A is equal to pi is what? Pi. Radius is diameter's half of it. Diameter is 0.5 into 10 power minus 3, right? Divided by 2 whole square. This will be giving us A. Now we will be given R is equal to rho L by A. Guys, you need some more time. Okay, you got it? Yes, let's see. A, B, C, or D. I'm expecting answers over here. Okay, so length would be how much? L. Rearrange. L is equal to R times A divided by rho. Okay, what is R? R, they are telling it should be having a 20 ohms, right? You want 20 into area of cross section pi. Okay, pi into 0.5 into 10 power minus 3 divided by 2 whole square divided by rho. What is the rho? Resistivity. They are giving you 1.6 into 10 power minus 6 ohms, right? So if you do it, you will be getting length, and the length would be in meters. I would be requiring this answer in the comment section, okay? Or shall we do it? Shall we do it? Just quickly tell me. Okay, if you want, I will be doing it. We have 20 into 22 divided by 7, right? 20 into 22 divided by 7 into, we have got what? 0.5 into 10 raised to the power of minus 3, right? Divided by 2, the whole square, divided by 2, the whole square. You should know how to do this because calculators are not allowed. Divided by 1.6 into 10 power minus 6, okay? 10 power minus 6. You'll be getting somewhere around 2.42 meters, okay? Well, options I had not given. So if you had, okay, options you have, no, 2.45, option B, okay? Option B is the right answer. 50-50. Why? What happened? See, this is important. This is very important. Those who gave between A and B, we can see we have 2.1, 2.45. So close, but still 2.45 is the right answer, okay? Option B. Only 𝐾𝐇 Agarwal gave the right answer. Let's see the leaderboard. Who is where? Indu Anup still in top 1. We've got Prabhakar top 2. We've got 𝐾𝐇 top 3. Shiva and rest all in the live chat. I hope this is clear, right? You'll be able to do it if this comes in the next class. Now, tell me which is in the right connection, okay? Now, ammeter, voltmeter, how that to be supposed to be connected, series, parallel and all. Immediate to this, I have got resistor in series and parallel. Just stay connected, okay? The question is, which is the correct connection, voltmeter or ammeter, okay? What is the correct way to connect an ammeter and voltmeter in a circuit? You will be telling me what is the correct way to connect a voltmeter or an ammeter in the circuit. A, B, C or D. Let's see, okay? I'm analyzing the circuit just for you, okay? Ammeter has to be connected in. Guys, do not just copy, just give me your answer, your opinion. Okay, Indu, just try and give me the right answer. Okay, I'm stopping the poll. See, here the ammeter is connected in series because the current is flowing, and the voltmeter is connected in parallel. So option C is the right answer. 66.66 has given the right answer. Great. Hats off to you. Here you can see your names in the leaderboard. Okay. Shall we go ahead and do resistors in series and parallel? Most important derivation, right? Let's do it. Resistors in series and resistors in parallel. Okay. Shall we do it, my dear students? Shall we do it? Great. Let's get to it. Series connection. First, you should know what series is. Okay. Series connection. Series means you will be connecting end to end. End to end connection is what we are going to call it as series connection. Okay. Now, how does the series connection looks like? Okay. How does the series connection looks like? Let's see. Now, imagine you have one resistor and the resistor is connected like this. Okay, sir, done. Fine. Resistor is connected like this. I'm explaining in detail. Everyone, look here. You have one more resistor. Another resistor is connected like this. Okay, sir, that's also done. So, how can we say this is series connection? See here. One after another. The starting point, ending point. The ending point is connected to next starting point. So, this is how we say the series connection looks like. End-to-end connection. I hope this is clear. Is it clear, Prabhakar? Is it clear? Yes, I hope it's clear. Now, let's say this resistor has got the resistance R1. Here we have R2 and here we have R3. Okay? Clear? Yes, sir, that's clear. Now, you should know one thing, okay? In series connection, in series, okay, current remains same, but what happens? Remains same, but the voltage divides, okay, but the voltage divides, okay, voltage divides. Okay, so what does that mean, sir? That means if a current I is flowing like this, same current will be flowing throughout, but across the resistor we will be having voltage V1, here we have V2 and here we have V3. Yes, sir, that is clear. This is how it works. Okay, to have a voltage, of course you will be supplying a voltage, my dear. Okay, total voltage you will be supplying. Okay, I hope this is clear. Okay, shall I just neatly draw this? Okay, how does this happen? You will be supplying a voltage and that voltage gets divided. Clear? Yes? Okay, sir. Sir, I did not understand volt. Okay, my dear, look. Prabhakar, focus. Imagine you are applying some supply, right? If you apply voltage, current flows. I told you before, right? What did I just say? If you apply voltage, see, if you apply voltage, the current flows. That I said, right? So similar to that, I'm saying, focus. I want you to understand. I want each and everyone to understand, okay? So if you apply some volt, what happens? You know, the entire voltage drops across resistor. That is the rule. That is how it happens in the nature, okay? So if you apply some volt, that gets dropped, divided, V1, V2, V3, that drops across the resistor, okay? I hope this is clear for everyone who's watching. So in series, current remains same and the voltage divides, okay? And how does voltage divides? Total voltage is divided into V1, V2 and V3. This is how it happens, Prabhakar, okay? So V1 plus V2 plus V3. Clear? I hope this is clear. Now, using Ohm's law, what does Ohm's law says? Okay, using Ohm's law, okay? Using Ohm's law. Let me copy this because we will be doing this in the next slide, okay? Using Ohm's law. Now, what's going to happen? Using Ohm's law, we can say that, what shall we say? Let me write it on the screen, okay? Just keep focusing, We know that V is equal to V1 plus V2 plus V3, right? Ohm's law says, V is equal to IR. Yes or no, Kriti? Very good, my dear student, okay? V is equal to I into R, right? Shall we write it everywhere? Yes, sir, we shall write. V is what? Total voltage, right? V is what? V equivalent or total voltage. So, V is equal to I into R. I equivalent, okay, is equal to V1 is what? Same current is flowing, but how much is the voltage? V is equal to I into R. V1 is what? I into R1, right? I into R1 plus what is V2? This I into R2 because the same current flows, right? I into R2 plus I into R3. The same current flows, I into R3. Clear? Okay, equivalent means, Prabhakar, that's total, okay? Equivalent means total. total. Clear? I hope this is clear. Okay. Now, what is same? I is same, right? I into R equivalent is equal to I is same. I'm taking I common. R1 plus R2 plus R3, right? So I gets cancelled. R equivalent in series. Okay. R equivalent means R total in series. What shall we write? R total is equal to R1 plus R2 plus R3. Okay. Similarly, if you have n resistor 4, 5, 6, 7, 8, 9, 10, it would be like similarly it goes till Rn. I hope this is clear. I hope it is clear for each and every one of you. If this derivation comes in your exam, will you be able to do it? Yes or no? Just give me a quick confirmation. Will you be able to do resistors in series? Yes or no? If you give me the confirmation, I can go to the next slide, my dear kids. Yes? If they ask you in the exam, will you be able to do? The main thing is current remains same and the voltage divides. The total voltage divides into V1, V2 and V3. Thank you, my dear students. Pakka. Prabhakar says, sir, Pakka I'm going to write. Okay. Thank you, Shamili, Indu, Anup, everyone. We are going to talk about resistors in parallel pretty soon. Okay. Resistor in series is done. Resistors in parallel we are going to discuss now. Okay. Resistors in parallel. Resistors in series is done, right? Resistors in parallel. Now, what happens in parallel is that we are going to use Ohm's law again to do this derivation. What law we are going to use? We are going to use again Ohm's law to derive that. But you should know what parallel combination is and how it is done. Prabhakar, don't worry, you say you're totally confused, but after this slide, of course, you will be super convinced that it's not pretty difficult, okay? Look, parallel combination, how it looks, I'll tell you. Take a resistor, okay, one resistor. Take another resistor, second resistor. Take one more, this is third resistor. Done. You've taken 3 resistors. Okay. Now, connect the starting points together and connect the ending points together. See, starting of this resistor, starting of this, all 3 are connected together. Yes, correct, sir. What about this? Ending point of first resistor, ending point of second resistor, ending point of third resistor. All 3 are connected to one point. So this is what we call parallel combination. Okay. So what kind of combination is this? This is the parallel. Okay. Parallel combination. And what are you supposed to do? Also kind of attach a power supply so a current flows, right? So the most important thing here is in parallel. See, what I'm writing now is very important. Focus in parallel. In parallel connection, okay? Parallel connection. What happens is the current divides in how many ever paths it's available. For example, if the current comes here, the main current is coming here. So it has 1, 2, 3, 4, 5 paths. It has got many paths. So the current divides accordingly. So I1 current flows through R1, I2 current flows through R2, and I3 current flows through R3. In series, voltage divides. In parallel, current divides. If you know this, the derivation is done. Okay. In parallel connection, current divides. Okay. The current divides. What does not divide? Voltage does not divide. Okay. Voltage does not divide. That means the same voltage, whatever you apply, would be there. See, the voltage, starting, ending point, everything is connected to the same point, right? So the voltage does not divide. I hope this is clear. Going to the next part, my dear students. Now, using Ohm's law. What does Ohm's law says? So how does the current divide? The total current I is divided into I1, I2 and I3, right? I is divided into I1 plus I2 plus I3, right? So what does Ohm's law says? You all know that Ohm's law says V is equal to IR, right? So what does Ohm's law says? You know, the Ohm's law says V is equal to IR. But what about I? I is equal to V by R. You know this, right? So what is I? I is equal to V by R. So let's see. I can be written as what? V by R. So V equivalent and R equivalent. Equivalent means total. Equivalent means what? It is total. Okay. Now talking about V equivalent by R equivalent. What is I1? I1 is equal to V by R1 because I1 current is going, voltage is same. What about resistance? R1, right? So we'll be having V by R1 plus V by R2 plus I3 is V by R3. So what is common here? Voltage is common. Voltage gets cancelled. The final thing what we got for Ohm's law in parallel is 1 by R equivalent is equal to 1 by R1 plus 1 by R2 plus 1 by R3. This is for only 3 resistors. If you have n resistor, R4, 5, 6, 7 connected, you will be saying, okay, you will be saying plus so on plus 1 by Rn. Okay, Prabhakar, why we are writing V numerator is, see, V is equal to IR. R goes below V. So I is equal to V by R. Okay, I hope this is clear, right? By numerator we have V. Is it clear? What's the final? We've got R equivalent as 1 by R1 plus 1 by R2 plus 1 by R3. Is it clear? Shall we do one small numerical on this and we will be wrapping up resistor in series and parallel? Yes, sir. Okay. Find equivalent resistances. Okay. So the question is find equivalent resistances. Okay. Resistances. Everyone, I want everyone to start doing it along with me. There will be poll for this for sure. Okay. So we have got 2 resistors. First one is like this is what kind of connection? This is 6 ohm, this is 3 ohm. Okay, so this is series or parallel. This is series connection. For series connection we have R equivalent is equal to R1 plus R2, right? So it is 6 plus 3 would be 9 ohm. Okay, for parallel I'll be giving you the pole. Very good, Kriti, very good, Prabhakar, everyone great. Okay, parallel, how does parallel looks like? So it would be like one resistor like this, okay, another resistor like this. Okay, now I'll be having one 12 ohm, another 12 ohm resistor. Okay, we are supposed to find equivalent. Is it series or parallel? Second case, it is definitely parallel, right? In parallel, okay, in parallel 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Guys, see what kind of mistakes you might do. You will simplify this and you will stop. Sir, this is done. This is 1 by R equivalent. No. Why? I'll tell you. See, 1 by 12 and 1 by 12. Okay. We'll take the decimal. So 1 plus 1 is equal to 2 by 12 is equal to 1 by 6. Sir, this is the answer, sir. This is the answer. 1 by 6 is the answer. Done. Do I get marks? No. No, no, no. Why? Because this is, guys, 1 by R equivalent is 1 by 6. See here, we've got 1 by R equivalent is 1 by 6. Is it the answer? No. Answer is reciprocal of this. 1 by R equivalent, you take the reciprocal, you'll be getting R equivalent would be 6 ohm. Do not make the mistake of stopping here. If you stop here, it's not the right answer. Thank you, Mukesh. Thank you, Prabhakar. Everyone, great. You know how to take reciprocal. Okay, so this is how. One shortcut is that when you have 2 resistors of same value, equivalent will be half of that. See here, you've got 12 and 12 here, right? So what's the equivalent? Without even doing this, you can say it is half of it. Clear? Is it clear, everyone? I hope this is clear. Let's go to the next part. Okay. Okay, resistors in parallel is done. Joule's law of heating. Numericals on whatever I do will be there. Only one unknown will be there. One unknown will be there, and that unknown you have to find it. Just practice, okay? Remember all the formulas. Remember what kind of numerical sir has done and try to form it, okay? Thank you, Prabhakar. At the starting of the class, you said, sir, series and parallel, I don't know. Now you tell me it's not clear. Crystal clear, right? Thanks a lot, okay? Now, Joule's law of heating is like, whenever you play games in your smartphones, it gets hot. Why do you think it gets hot? Because of resistance, okay? Because of the electrons going to go and collide into the particles, heat is generated. Okay, now we are going to discuss about that. Okay, the amount of heat, the amount, okay, the amount of heat generated, okay, the amount of heat generated due to flow of electric current, okay, flow of electric current, flow of electric current. How much heat is produced is given by Joule scientists. Okay, the amount of heat generated due to flow of electric current, okay, is proportional to three things, my dear students. Is equal to see, heat generated would be equal to H is equal to square of current, resistance, and the time for which it would be flowing for. Okay, right? So I hope this is clear, right? Is equal to square of current. Okay, I'm going to continue writing this over here. Is equal to square of current flowing through it. Okay, current flowing through it, flowing, resistance, okay, resistance of it, and for the time for which it is flowing, okay, is equal to product of, okay, we are multiplying, right? It's like product of. Okay, I hope this is clear. Okay, sir, if series and parallel are given in circuit, we should find the resistance of series first or parallel? My dear, it's like try to simplify the circuit by doing parallel first and then do the series. Okay, that's how you do, Mukesh. Okay, Prabhakar, yeah man, you touched my heart. Okay, do not cry. I can understand that you understood series and parallel. I hope this session is helping you a lot. Okay, बताइए पास होने का formula, all the formulas of electricity will be helping you to kind of pass in physics. Bio and chemistry, different formulas there. Okay, so this is H is equal to I square RT. What is this? This is Joule's law. Sir, are there different forms to write? Yes, remember we have three forms of Joule's law of heating. Okay, how can we write it? See, how much ever heat is produced depends upon the work done. Okay, so or else you can just see here, or I can write the three forms of Joule's law of heating. Okay, Joule's law of heating, three forms I will write. Okay, first form you got to know that, what is that? H is equal to I square RT. This is the first form. Okay, okay sir, what is according to I? See, according to Ohm's law, V is equal to IR, I is equal to V by R, and R is equal to V by I. You know this, right? This is because of what? This is because of Ohm's law. Yes or no? Yes or no? Yes sir, you are right. Now, if we put I is equal to V by R, let's see what do we get. Okay, H is equal to, I am going to put V by R. V square means I square R square into R into T. So what happens? R square, R get cancelled. So H is equal to V square by R into T. This is second form. Remember, this is first form, H is equal to I square RT, and this is second form, H is equal to V square R into T. Now, if you put R is equal to V by I, R is equal to V by I, let's see what we'll be getting. H is equal to I square, R is what? R is V by I, so V by I into T. So I gets cancelled, VIT. Can you see? H is what? H is equal to VIT, right? So I'm going to highlight this as well. H is equal to VIT. Three formulas did you get? H is equal to I square RT, H is equal to VIT, or H is equal to V square R by T. All these three formulas you can use to do numericals. If you do not know any one of the term, do not try to find the other using Ohm's law. See, there are two ways to do Joule's law of heating. If one is not given, use Ohm's law, find one and use one first formula. Don't do that. We don't have enough time. Use either of these formulas to go through the what? All the numericals what you might get in your board exams. Clear? Is it clear, my dear students? Joule's law of heating? Yes? Okay. Now, we have a question on Joule's law of heating. Well, how much time I will be giving you? A 120-second poll has been started. Go ahead and quickly give me your answer. So we'll solve this. A girl turned on a room heater of resistance 50 ohm. They are telling a girl has turned on a heater of resistance is how much? 50 ohms, okay? Which operates at 200 volts. Voltage is 200 volts. For time, it is like 20 minutes. What are we supposed to find? We are supposed to find heat dissipated, okay? Okay, we are supposed to find heat dissipated. Prabhakar, coming back to you, okay? So heat can be given by V square by R into T, right? You can see here, heat is what? V square by R into T. This is what we can use. There is no need to use current formula. Why? No need to find current. So time is 20 minutes. 20 into 60. Why 60? We are taking it seconds. 1 minute has got 60 seconds. Like that, we've got 20 minutes. 20 into 60, right? Okay, great, my dear students. Now, H is equal to what is V? V is 200, right? 200 square. 200 square divided by R. R is 50, my dear students. 50. And time is 20 into 60, right? 20 into 60, right? So if you do this, you'll be getting the answer. Go ahead and quickly tell me, okay? Oh my God, Prabhakar, I touched your heart, I guess. Thanks a lot for the compliments. Well, thank you, man. Thank you. I just want one thing, guys. You all have to do great in your exams. That's all I want, okay? So A, B, C or D, how much you'll be getting heat? They are giving in kilojoules, okay? Kilojoules. What is kilo? Whatever 3 zeros you'll get, that is written in K. That's all, okay? Guys, quick. Just give me your answers super quick because we are running out of poll time, okay? So I'm going to end the poll. So if you do this, you will be getting 96. See, how much you'll be getting? I'll write 960,000 joules because SI unit is what? SI unit of joules. It can be written as 3 zeros can be written as kilojoules, okay? So 960, these 3 zeros can be written as kilojoules, okay? So option B is the right answer. Most of you have given the B. Let's see. 100%. Great, my dear kids. So top two, we have got Shamili and Indu Anup at leading position. Clear? I hope this is clear how to do numericals on Joule's law of heating, okay? Next, talking about applications of Joule's law of heating. Well, Joule's law of heating, is it bad, sir? No, we can use it in a good way where for the fuse, okay? Well, what fuse does is that fuse, okay, fuse helps, okay, to protect circuit, electric circuit, okay, electric circuit. What does fuse helps, my dear students? Fuse helps you to protect electric circuit. How does it do, sir? This works on Joule's law of heating, okay? This works on Joule's law of heating, okay? Joule's law of heating, okay? Now, how does this actually work, okay? Let me explain, okay? Now, here, imagine this circuit, okay? This bulb works until you've got 5 amps of current. If 5 amps of current is flowing in the bulb, bulb will not be busted, okay? Next, talking about the capacity of the wire. Wire also supports up till 5 amps, okay, fine. Now, what if this voltage, if this battery will be giving you 20 amps, okay? What if it kind of pushes 20 amps? So in that case, we don't want the bulb to burst or the wire to burn, right? So we are going to use a fuse, okay? What is this? Fuse. What does the fuse do? When the current is beyond 5 amps, it melts. Fuse is so cheaper, okay? This fuse is there. No, this is so cheap than bulb, okay? It's like available for 5 rupees and all, okay? Now, what does this fuse do? Fuse melts when current, okay? When current is above, where? Above 5 amperes, thereby saving the circuit, okay? So this is how it happens, okay? Mukesh, sir, what about resistivity, sir? Will you take that concept today? Yeah, resistivity is done. No, resistivity we discussed. Resistivity is how much resistance over given meter. That's what is resistivity, okay? Simple concept. That's done, my dear student, okay? If you still have doubt, you can ask me. So what does fuse do? The fuse melts if the current is above 5 amps. 5 amps is rated current, okay, allowed current. It works on Joule's law of heating. After it melts, what it does not allow any other current to flow, thereby saving the circuit. It protects the circuit, okay, protects the circuit. Clear? Is it clear, my dear students? Any doubt? If you have any doubt, you can kind of ask me in the live chat. I'll be helping you out, okay? Yes, I hope that's done. Talking about electric power. See, electric power is how much energy is transferred within the circuit. Rate of transfer of electric energy within the circuit. Okay, power, okay? Electric power is defined as rate of transfer of energy, okay? So it's like how quick you can do the power, okay? How quick you can do the work, okay? Work done by time. So power is given by P is equal to V into I, where V is voltage, I is current. And you can write, according to Ohm's law, P is equal to I square R, or P is equal to V square by R. How did you write this, sir? Using Ohm's law. See, V is equal to IR, right? So instead of V, I'll write IR. So I into I square into R, I got it. Next, instead of I will write V by R. So V into V divided by R. This both using Ohm's law. Using, Ohm's law. How did we do that? Just like how we did for power. See here, for power, we used I is equal to VR and V is equal to I by R, right? So that's why it is, okay? Right, let's do some numericals, Prabhakar. Don't worry, if you are confused, that would be taken care of today. Okay, talking about commercial unit of electricity. What does commercial unit of electricity says? Now, whenever you kind of use electricity in your house, what's going to happen? You're going to pay bills, right? You're going to pay bills for the electricity what you have used for. So how much to be paid, sir? Well, that depends on how much you use. That's measured in units, okay? Commercial unit of electricity is measured in units, okay? Units. And 1 unit of commercial unit of electricity is equal to kilowatt hour, okay? How much is that? Kilowatt hour. So kilo means what? 1000, okay? Watts, yeah, it's just watts. What about hour? 1 hour has got, 1 hour has got 60 minutes and 60 minute has got 60 more seconds, right? So 60. So 1 unit of electricity would be giving you 60 into 60, 3600, followed by 3 zeros. So you can write it as 3.6 into 10 power 6 joules, right? So this is how the commercial unit of electricity is. Commercial unit of electricity is measure of how much energy is used. So 3.6 into 10 power 6 joules will be giving you 1 unit, and 1 unit is the commercial unit of electricity. Is it clear? If you get numerical on this, I'll show how to solve. Just stay with me, okay? Next. Let's do this numerical on commercial unit of electricity. Once I do this, you will be kind of super satisfied with this chapter, electricity, so that we can go to the next slide, okay? This is on commercial unit of electricity. Commercial unit of electricity, okay? This is commercial unit of electricity. What's the question? Well, before that, I'll start timeless poll. There is no time for this. The poll has started. You can give the answer. We have a house, and what's happening in the house here? Okay, what part you're not understanding, please let me know. I'll repeat, okay? An electric refrigerator is rated at 600 watts. So they are saying that the power of this power is how much? Power is 600 watts, okay? Operates 16 hours a day, okay? How much time it operates? T is equal to 16 hours a day, okay? What is the cost of unit? What is the amount? So we should find how many unit is used here and multiply by cost of 1 unit, okay? So let's see, okay? Let's see what's the answer, okay? Now, what is the cost of energy to be operated for 60 days at 5 rupees per hour? 5 rupees for 1 kilowatt hour. Let's see, okay. So 16 hours can be written as 16 into 60 into 60 seconds. Why? 1 hour has got 60 minutes, like that we've got 60 seconds, and we've got 16 hours like that, okay. Take everything in SI unit while solving because that's very important, okay. T is equal to 16 into 60 into 60. Clear? I hope this is clear. Now, we're supposed to find what is the amount of electricity, okay. See, 1 unit is equal to 1 kilowatt hour. So how many units are there? How many units are there? Let's see. See, we have got 600 watts, right? 600 into kilo, let's find it out. Hours, how much? 16 into 60 into 60. So this will be giving you how many units we are kind of using it. Shall I do it for you, my dear students? So 600 into 16 into 60 into 60. You'll be getting how many units? Here you'll be getting 3, 4, 5, 3, 4, 5, 6, 0 units, okay. Okay, this is like kilowatts, right? So the answer you're getting is number of joules, okay. Number of joules you're getting is 3, 4, 5, 6, 0, 0, 0, 0 joules of electricity. But how many units? Let's find it out by dividing. Units is divided by, you do 3.6 into 10 power 6. That will be giving you number of units, okay. So this divided by 3.6 into 10 power or 36, that's 9.6 units. How much is he using? 9.6 units. What did I do here? This is for 1 unit. So number of joules. Divide total joules by 1 unit, you will be getting number of units. So these many units they are using. 9.6 into for 1 kilowatt hour, okay. So for 1 unit it is 5, right? 5 into 9.6, if you do 9.6 9.6 into 5, you'll be getting how much? It's not actually 9.5, is it? Okay, can you see where we are going wrong? Can you just check where we are going wrong? See, I'm going to kind of repeat it once again. These many joules, right? So 16 hours a day. Okay, one more 60 is missing. See, for 60 days he uses, right? Into 60 you have to do. This is what? This is days, right? So so what has happened is you have missed 160, okay? So remember not to do that. Into 5 rupees. So 2880. Guys, what we had removed is this 60 days you had not included. See, such silly mistakes you cannot do, okay? So 9.6 watts for 1 day. This is for 1 day, right? Like that you use 60 days and 5 rupees per hour. For that you will be getting option C, 2880 rupees. Did you understand how to do? Okay. Did you understand how to do? 100% of you have given the right answer. Hats off. Sir, how to calculate that much time it will take whole exam? Yeah, my dear student, it will take that much time. But such a big question, see, all zeros you have. 1, 2, 3, 4 zeros you have. 4 zeros here get cancelled. It kind of, they'll be giving you an easy question. Do not worry. Sometimes it might happen, okay? Don't worry. Well, seeing the leaderboard, great Hindu Anup still maintaining the streak, top 1. We've got Kriti, Shiva, Prabhakar, everyone else in the session. Okay, done. This kind of question will be there will be asked for your exam. One last concept is there, that's overloading. What's overloading? It's like if you connect lots of components in a single plug, that's what is called overloading. Okay, see, overloading causes short circuit, okay. Overloading causes, overloading is like plugging so many appliances which requires lots of energy or lots of current in very small, in a very small circuit, okay. Overloading causes heat and damages the entire circuit itself and damages the circuit. Actually, sir, what is overloading? See, I'm going to tell you what overloading is, okay? Imagine you have a circuit like this, okay? You have a TV over here, and you have a bulb over here, and you have an AC over here, okay? And you have a supply, okay? You have a voltage supply over here. In this case, okay, you're connecting everything to one same point, and wire has capacity to handle. See, you have wire all over, right? The wire has capacity, okay, capacity to handle only 10 amps of current. Let's imagine only this is the capacity, but see, TV takes, let's say, 5 amperes of current, and AC requires, bulb requires another 3 amperes of current, and AC requires 20 amperes of current. If you add 20 plus 5, 25 plus 3, 28. So what's going to happen? Due to the heating effect, the wire will burn, right? So capacity is 10, but here we are getting 28 amps. This is going to heat and melt the wire. Heat and melt the wire. So this is what is overloading, and overloading should not happen. For that, what you should do not connect lots of things for a single plug, okay? It might also cause overloading, okay? So overloading can cause short circuits and the wire to burn. Clear? Is it clear? One small last concept for today. That's domestic circuits, okay? After this, we'll be taking first two chapters. First chapter is pending, second chapter is pending. So we will take that super quick. Just listen. Why is series arrangement not used for domestic circuit? Okay, let's answer this question. Okay, okay, this is very simple. Imagine you have a bulb over here. Okay, imagine you have a bulb over here. Okay, series connection means end-to-end connection, right? One after another. First TV is there, and then bulb is there, and then next is there. It's like end-to-end connection, okay? A bulb is there, and you have a TV over here, and you have an AC over here, okay? And you have okay, you have a grinder. In the middle, you have grinder, okay? You have, one second, guys. You have what here? Grinder, okay? Grinder, and you have AC over here, okay? You have AC, and you have TV over here, and that's all. This is how the series combination looks like. Series combination means what, my dear students? End to end connection, okay? So in this kind of connection, let's see, you are going to watch TV, okay? You want to watch TV. What's gonna happen? You want to watch TV, but with that, you have to turn on AC, because see, TV requires what? TV requires current, right? It requires a current. The current will not jump from here to the TV. It has to take a path so that it actually flows like this, right? It has to, you have to turn on the bulb. If you turn this off, no current goes further, so you cannot use. So turn on the bulb, turn on the grinder, turn on the AC, then the TV works, okay? So how much extra unwanted things we are running here? Not required, right? Okay, this is bulb, my dear students. What did you write in that circle? This is bulb, okay? Okay, this is supply. This is supply, okay? Imagine a battery, or you can represent like this, okay? Clear? Now, to operate TV, you want to use 1, 2, 3, everything. Is it possible, right? So, okay, so that is one disadvantage. Or next, imagine the AC is failing, okay? Failing, that means Kriti, yeah, very good for bringing this point up. So if AC is failing, no current goes beyond AC. What if you want to watch TV? You want to find a guy who fixes the AC, and then you can watch TV. No, right? Unnecessary stuff. Or if, imagine, TV wants 6 ampere of current, it requires 6 ampere of current. What about bulb? It can just work in 2 ampere. If imagine 6 ampere of current flows through that, it's going to burn the circuit, right? So we are not going to use series arrangement. Instead, we are going to use parallel arrangement, where we can independently operate the equipments. If one fails, the other will be working independently, and it does not cause overloading. Got it? Is it clear? Thank you, others. Diamond clear. Is it Is it that? Okay. PW English Medium 9th and 10th. Thanks a lot. Okay. Why series arrangement is not used in domestic circuit? Well, these are all the things you will write. We cannot operate with, okay, shall I write it? With the series connection, we cannot operate all the things independently. Dependently it works. If one device fails, the other thing will not be working beyond that. Very good. Okay. If one fails, others, yeah, other is not going to work. And the third thing, if one at the end requires high amount of current, the rest, if the same current flows, it's going to kind of burn the circuit and the circuit is going to damage. Okay, clear? Yes. Right. Now, before we go to the first chapter, I will be giving you small time. Okay, of course we are doing this from past 3 hours without a break, so I'll be giving you 10 minutes of break. Just go have some small snacks with you. Of course, not go, just go for a dinner, have some snacks, have some water, and come back. Okay. Two more chapters are there. I'll be back soon. So guys, I'll be back soon. Okay guys, I'm back, but we've got only 2 more chapters left, which we will be discussing pretty soon. Let the timer end. Only 2 chapters are left, right? Only 2 chapters are left. Waiting for timer to end because I want everyone to be in the class. On time, yeah, before time. You also are on time. Okay. Guys, going to the first ever chapter for the day, that's light, okay? Remember the chapter light reflection and refraction, right? So light reflection and refraction, what's going to happen is that here we are going to talk about all the different laws of reflection and refraction. Hi there, hi for everyone who is back. Just give me a moment, it's saving. So that, yeah, everyone are on time. I am on time. I hope, did you kind of just keep a timer? Okay, so what's the main difference between ampere and volt? See, ampere is the amount of current, volt is amount of voltage, okay? Right? Is it clear? It's taking a lot of time to save. Well, I hope this is clear. Now let's go to the first ever part where we talk about real and virtual images. See, when we talk about light, real image and formation of images, real images are those what you can get to kind of see on the screen. Virtual images where the images cannot be got on the screen, okay? Yeah, so let's kind of go ahead and talk about different things, real and virtual, right? So real images, you know, the images which can be caught on the screen, okay, can be caught on screen, okay? What about virtual images? Virtual images are those which cannot be caught on screen, okay, which cannot be caught on screen. That means, see, in movies and all, the projector light falls on the screen and you can see that. But in the case of mirror, when you see yourself, that is not kind of will be visible inside the mirror, right? Right. So that's what it is. Now, what are the laws they might ask you in the chapter? You've got 2 laws, right? What does first law says? The first law says, see, the incident light ray, the light ray which is kind of coming and falling on the reflecting surface will kind of reflect, right? Yes, sir, that will reflect. And if you draw an imaginary line perpendicular to the reflecting surface, we are going to call that as normal. If you measure the angle between incident light ray, incoming light ray, and the normal, and reflected light ray and the normal, the angle will be same. So here it is θ1 is equal to θ2, or you can write I is equal to R. So this is the first law of reflection, okay? What about the second law of reflection? It says that incident light ray, reflected light ray, and normal, everything lies on the same plane. What does plane means? Imagine the point of the pen is lying on my hand. If I kind of put it like this, the starting point is over here and the ending point is not there, right? That's what a plane is. So first law says that, and what does second law says? The incident light ray, reflected light ray, and the normal lie on the same plane. This is what is laws of reflection. They will be asking you. Now, what are the different terms related to spherical mirror? Well, listen carefully. It says that pole is the center of part of the mirror body you have considered, okay? You've considered this mirror. If you take the center of that will be giving you the pole. What is center of curvature? Center of curvature is a center point which is required to make an entire spherical mirror. And from center to the pole, that's the radius of curvature. And if you take half of it, that gives you the focus. Focus is half of the radius of curvature itself, right? Now, this is about the different terms related to spherical mirrors. If you talk about principal axis, an imaginary line which draws center of curvature, focus and pole will be giving you the principal axis, okay? So this is about the different terms related to mirror. Now talking about concave and convex mirror, well, see here, concave mirror, the reflection happens on the cave part, and convex mirror, the reflection happens on the bulged part, okay? Now, if you see here, I'm going to tell you which is concave and which is convex. Just by seeing at this, you cannot say whether it is concave or convex. The reflection is what decides, okay? Now, imagine I'm going to rough this part out. Rough in the sense, it is not so reflecting surface, it is rough surface, okay? Now, the reflection happens on the cave part, right? So this is what we are going to call it as concave mirror, okay? This is concave mirror. What about convex mirror, sir? The convex mirror looks like this, where the reflection happens on bulged part, okay? Bulged part. This is convex mirror. Whenever it comes to convex or concave mirror, you will be given ray diagrams. How to form ray diagrams? What are we supposed to do? Let's see, okay? Right, you should require some special rays to draw ray diagrams. Only two rays are required, which after reflection meets, there the image is formed, okay? Now, what is one special ray? A light ray which is going parallel to the principal axis goes through focus. First special ray. A light ray which is passing through focus goes parallel to the principal axis. Second special ray. Third special ray. A light ray passing through the center of curvature after reflection passes through the center of curvature, okay? Now, if angle of incidence, it's making some angle of incidence, it reflects with angle of reflection. Guys, see here, concave mirror, this is convex mirror, okay? Do not get confused. Bulge part is convex, okay? Now, how does the image forms in different cases? Always remember, in the case of converging, concave, okay? Concave is the case of converging, okay? Converging. What happens in converging? You'll be having 6 cases where the image will be forming differently for all 6 positions. How does it happen? When the object is kept at infinity very far, okay? So, see, the object position, it is kept at infinity. Image, where is the light rays after reflection meeting? They are meeting at the focus, right? So, image position at focus. Now, what is the image size? It's so tiny, point size. So, we can write it as point sized, right? Nature of image. Whenever two light rays actually meet, we are going to call that real image, right? Hello there, unknown mystery. How are you? Okay. Yes. So the nature of image, that is real image. Why it is real image? Because the light rays after reflecting are actually meeting, right? Now, try to bring the object a bit closer, beyond C, okay? Where is the object? Kept beyond C. Now, what happens to the nature of position? Can you see? It is between C and F. So, image is forming between C and F. Okay. Nature of image. Well, nature is still real. Why? The two light rays are meeting, right? So, image size, it is small. That is diminished. Okay. What we shall write? It is diminished. Okay. It is diminished. Now talking about whether it's real or inverted, two light rays. Can you see? After reflection, it is meeting here. Another light ray, it is also meeting. So it is real image. Now what is the trick you might want to know here is that after reflection, how does this happen? Where does it meet? Wherever it meets, that's where we get to see image. Okay. Now try to bring at C. Okay. See, whenever you keep the object at C, there might be a small issues at the exam because it will not exactly meet here. So remember, whenever you keep the object at C, the image will be forming at C itself. Got it? Right. Now, image position, when you keep the object at C, the image will be forming exactly at center of curvature itself. What about size of the image? Same size of the object is equal to size of the image, right? So, same as object. Got it? It is kind of same as object. Talking about nature of image, two light rays after reflection, they are kind of meeting together, right? So they are again forming a real image. Okay, this is how you are supposed to remember. What are the other two cases? Between C and F. Whenever you keep an object between C and F, one light ray goes parallel to the principal axis, passes through the focus. What's the special ray? The one which is passing through the focus goes parallel to the principal axis. Where is it moving? It is object is kept between C and F. Image is forming beyond C. Is it real image? Yes, indeed, because they're meeting, right? Similarly, over here, what happens is that these light rays meet, but at infinity, kind of very far. So we say it is real image, super highly enlarged. Okay. Now, talking between F and P. Okay. Focus, Prabhakar. It will be easy, okay? Now, you are keeping an object between F and P. What is happening here? One light ray is, we are using fourth special ray. It is making certain angle of incidence. It reflects with certain angle of reflection, okay? Now, you take another special ray which is going through the center of curvature. What's going to happen? It is kind of diverging here, right? So, sir, do you think they're not meeting? So, image is going to form? Indeed, image is going to form. But where? If you extend it virtually, here light rays after reflection are not meeting, right? So virtual meeting is happening, so we get to see virtual image. So if you see the size of the object and image itself, the image is bigger, right? So it is enlarged, we can say enlarged, okay? This is a case of concave mirror, okay? What about convex mirror? Convex mirror is simple, my dear student. Here, reflection happens on bulge part. What are the special rays we use? The ray which is passing parallel goes through the focus, but of course, it cannot go through focus. It diverges as if it going through the focus, okay? Next, if it is it is incidenting through focus, passes parallelly. It is going through the center of curvature, it passes with the same angle, and it's making certain angle of incidence reflect with certain angle of reflection. Siva, you have a question. Sir, why do we take the flow of proton as current? Wasn't it past assumption? Well, that's a good question. See, based on past assumption, they have created the entire circuit. If they want to change it, they have to rewrite all the books. Everything has to be reimagined, which is very, very, very difficult. So this is how they do it, okay? It's considered already, okay? Now, now the thing is how the image formation how happens. See, this is kind of diverging, right? This is a diverging mirror. Remember, either mirror or lenses, diverging we will be having only 2 cases. Converging will be having 6 cases, okay? Diverging will be having 2 cases. If the object is kept at infinity using the special rays which is coming parallel, as if they are going to meet at focus, they diverge, right? So where are they meeting? They are virtually meeting at focus, and the image is point size. Remember, all virtual images will be upright and not inverted. Over here, you keep anywhere apart from infinity, okay? So here what is happening? Take a light ray which is going parallel, it will diverge as if the light ray is coming from the focus according to special light ray. Another one which is going through center of curvature passes through the center of curvature. So what's going to happen? The image is going to form such a small way between P and F, that's imaginary, and virtual images will be always upright, okay? Sir, can we use various rules to draw image formation? Yes, my dear students. See, you've got special rays, right? You can use any of these special rays that will be helping you out to draw this, okay? Right. Sir, what is sign conventions? Well, sign conventions are very important. You might be having so much confusion regarding sign conventions. In an easy way, if you want me to tell, as simple as that. First thing, all the signs are measured from pole, okay? All the signs or the distances are measured from the pole. Now, if you can see here, we are keeping an object over here. There is an object and the light rays are coming like this. Now, if you measure in the same direction of the incident light ray, it's taken positive. But light ray is coming in this direction, sir. Shall I just use it in the, what if I measure in the opposite direction? Well, that's negative, okay? So, if you measure in the opposite direction of incident light ray, see, light ray is coming like this, but you're measuring in the opposite direction, that's negative. Similarly, if the light ray is coming like this and you're going to measure in the same direction, then we are going to call it as positive. If you want to say it in a small simple way, we can say that, how can we say that? If you measure towards the object, that's negative. See, from pole, if it is measured towards the object, from pole, if you measure towards the object, okay, if you measure towards, okay, if you measure towards the object, how does it look like? Towards the object, okay, it's negative. It's always negative when you measure towards the object. But if you measure the other side, that's positive. Remember, this is the same with lenses and mirror. Do not get confused. Left is positive, right is negative. Not like that. It's based on sign conventions, okay? Now, going about laws of refraction. how does laws of refraction works? Well, laws of refraction, we have got two laws. What's the first law? The first law of refraction says, we've got like Snell's law, right? So the Snell's law says that the first ever law, that is Snell's law of refraction. That's uh, Snell's law. So what might happen here? It says that the sine of angle of incidence to the sine of angle of refraction is a constant, right? So what does Snell's law says? Snell's law says the sine of angle of incidence to the ratio of sine of angle of refraction is a constant. How does this work, sir? See, imagine a light ray is coming like this. After refraction, it bends, right? So how does that bend? That's what is going to give us that, okay? See, angle of incidence is how much it is making, okay? Angle of incidence is I, angle of refraction is R. So sin I by sin R will be giving you constant. This is our first law. That's Snell's law. What's second law, sir? The incident light ray, refracted light ray, and normal, everything lie on the same plane. That's our second law, okay? So refraction is just like bending of light when it moves from one medium to another medium. That's refraction, my dear students, okay? Now, talking about refractive index. See, refractive index is measure of a factor by which the speed of light is changing when it moves from one medium to another medium, okay? So it's like the definition is refractive index, okay? Let me just change the color of my pen. Refractive index is, see, whenever the light is moving from vacuum to any other medium, the speed changes because the speed of light is maximum in vacuum. Any other place, it's so less, okay? So refractive index is a measure of factor by which the speed of light is changed when it moves between two different mediums, okay? So usually that gets less when it is moving from vacuum, or else it will be same, okay? So refractive index can also be said by speed of okay, absolute refractive index. Let me talk about something called as absolute refractive index, which is very easy, okay? Whenever you're comparing with the vacuum, that's what we say, absolute refractive index, okay? What does absolute refractive index says? Absolute refractive index says it is the factor by which the speed of light is reduced when it is moving from two different mediums, okay? So in fact, what's going to happen is that absolute refractive index, it's like whenever a light is going from vacuum to any other medium, how the speed is changed, okay? It's the factor by which the speed of light is reduced in a medium when the light goes from two different mediums. So it is given by speed of light in vacuum divided by speed of light in medium. So this is what is absolute refractive index. So if you see here, the refractive index in air or vacuum is 1. That means the speed is maximum over here. As the refractive index increases, okay, as the refractive index increases, can you see speed is reduced? So what can we say? Refractive index is inversely proportional to speed. If the speed increases, the refractive index reduces, or if the refractive index increases, the speed reduces, okay? I hope this is clear. See, it is 1.44. So in oil or in kerosene, the speed is less. Look at the diamond. Refractive index is so high, the speed is so low, okay? This is how you do refractive index. If they give you numericals, you will be able to solve it. Is it clear, my dear students? If they give you such questions, will you be able to do it? Yes or no? Just give me a thumbs up whether you will be able to do this in your final exams whenever they give it. Yes or no? Tell me, my dear students. If that's done, I will be kind of going to the next session, okay? Shall I go to the next part, my dear student? Clear? I hope it's clear about refractive index and absolute refractive index, okay? Now, let's go and talk about how the bending happens, how the refractive index bending happens, okay? Now, imagine you've got two mediums, okay? You've got two mediums. One is denser and one is rarer medium, okay? One you've got rarer medium, one you've got denser medium. Let's see how the bending happens. I'm going to teach you a short trick how you can remember denser and rarer mediums and how the bending happens, okay, refraction happens. Let's take, we have air over here, okay, you have water over here. You know, air is optically rarer, water is optically denser. When the light ray is moving from optically rarer medium to denser, this is what? Rarer, right? This is denser. It bends towards normal. What is normal? Normal is a perpendicular line, right? Normal is perpendicular line drawn, right? So from rarer to denser, it bends towards the normal, okay? From rarer to denser, it will be bending towards the normal. So how can you remember this? This is rarer to denser, it bends towards RTD, okay? Is it clear? I hope this is clear. uh, Aurora sensation says from rarer to denser, it bends towards the normal. Shall we see what's going to happen if it bends from denser to rarer? Let's take another example where we have, you know, I'm going to take two different mediums. So this is medium 1, okay? And I'm going to take another medium, that is medium 2, okay? So here what I do is that I'm going to take a denser medium here, okay? Imagine I have got water, okay, and I've got air over here, okay? I'm going to point a laser light. When you point a laser light, the light is traveling from denser to rarer. Water is optically denser. Air is optically rarer. What's going to happen? It bends away the normal, okay? This is what? This is normal, right? This is our normal line. It bends away the normal, right? This is how the bending is happening. So what shall we do it? Okay, we shall say here, we shall say it bends away the normal. So DAR. See, denser. Water is denser medium. Air is rarer medium. It bends away the normal. So DAR. You remember like this. G, A and R. Is it clear, my dear students? Yes. This is kind of better trick how to remember, okay? I just tell this is better trick. Yeah, this is kind of better trick. So remember, from rarer to denser, it bends towards. Rarer to denser, it bends towards normal. Similarly, from denser to rarer, it bends away the normal. So this is how you remember. Clear? Is it clear? Thank you, my dear students. Now let's go to the next part. So here, let's talk about types of lenses, okay? So we've got two types of lenses, concave and convex lenses. Concave lens is like this, it is diverging part. So what is concave? It is diverging, okay? Diverging. Concave lens, concave mirror is converging, concave lens is diverging. Remember, here we have convex lens. What does convex lens does? Convex lens is kind of converging, right? It's converging. Now what happens in converging and diverging is that, see, convex lens converges the light. Whatever light passes through the convex lens will be converged at a point. Similarly, whatever light is kind of passing through the concave lens, they diverge. So always for converging we'll be having 6 cases. For diverging we'll be having only 2 cases, right? So let's see the ray diagrams for this. But before that, know what are the special rays. One of the special ray you might require to draw ray diagram for convex lens is that a ray is coming parallel to the principal axis that passes through focus. What's the next ray? A light ray which is passing through the optical center, just refracts through the optical center, okay? Speed किसमें ज़्यादा होगी? Well, the speed of light is maximum in vacuum. Rest all, whatever you take, the speed is less than vacuum itself, okay? Is it clear? Yes. Now, let's see what are the 6 cases in convex lens. See, convex is converging. As I said, we've got 6 cases for converging. What are those 6 cases? An object kept at infinity. When you keep... okay, I've got one more question. Which shows the medium is denser or rarer? Yeah, refractive index shows whether the thing is whether the medium is denser or rarer. If it is more, refractive index is more, the density, optical density is more, okay? Now talking about how the image is formed. When you keep the object at infinity, after refraction it is meeting at f2, right? So image position, it is at f2. What about image size? It is point size. Can you see it is just a small single point, right? It is point sized, okay? Point sized. Image nature, they are really meeting, so it's of course it's real images forming over here. It is real image which is kind of forming. Similarly, we've got many other cases as well. And let me discuss one more case, okay? What happens when the object is kept at 2f1? Take one parallel ray which is going through the focus. Take another ray which is going through optical center, just refracts like this, okay? So now, talking about this, where are they meeting? They are meeting at 2f2. Here also, the image position is at 2f2. f2 is different, 2f2 is different, and nature of image, it is real image. Size, can you see, it is same as object, right? Same as object, okay? Clear? Is it clear? Okay, difference between optical density and refractive index. Well, refractive index talks about optical density. If refractive index is more, the optical density is more, okay? Well, refractive index, my dear students, that Prabhakar, he is asking, well, I already discussed, you can, go back and kind of see what refractive index is. See here, I've discussed what refractive index is. It's like which is how the speed of light is differed when the light bends from one medium to another medium, okay? We have got other three cases for convex as well. Look at the place where the actual rays are meeting. Wherever they meet, that's where the image is formed. When the object is kept between 2f1 and f1, take the same special rays, see where they are meeting, then you can decide where the image is happening, okay? Yes. What's your question, Queen? I've got Queen 637. What's your question? Go ahead and ask your question. I'll try to clear it, okay? Yes, another one. When you keep the object between f1 and O, what's going to happen? They're not going to kind of meet after refraction, right? They are going to meet virtually. So here virtual image is formed, okay? Ray diagram is the easiest one. Yes, magnification of image, yeah, we are going to discuss soon, okay? In case of concave lenses, it is only two cases are there because this is diverging. In diverging, how many cases do we have? Only two cases do we have. And what are those? Well, those are like when it is kept at infinity, the light rays which are coming parallel diverges as if it is going from focus according to the special rays. Where is the image position? Image is happening at f1. What is size? Can you see how small it is? It is point size, right? It is point size, okay? It is point sized. What about image nature? Are the light rays actually meeting? No, sir, the light rays are not actually meeting. So what kind of image is forming here? Here it is virtual, okay? Here virtual image is forming. In diverging cases, my dear students, only virtual image forms. Let it be lens or mirror, okay? So this is how it happens. Here also, anywhere other than that, the image is forming virtually, but it is pretty small, right? So this is about image formation, okay? In mirror and lenses. Talking about one small thing, the same thing what I said, that is regarding the sign conventions. As I said, where is the object, my dear students? Object is kept over here, okay? The incident light rays are coming in this direction. If you measure in the same direction of incident light rays, we are going to take it as positive. But just in case, if you try to measure in the opposite direction, see, incident light rays are coming like this. But if you measure in the opposite direction, it's taken as negative. Clear? This is for both lens and mirror, okay? But in mirror, measured from pole, but here it's measured in optical center, okay? Sign conventions, yeah. See, it's like if you measure in the same direction of incident light rays, positive, opposite direction, negative, as simple as that. Very simple it is, okay? Or another way how to remember, if you measure from optical center towards the object, negative, away the object, positive. Do not remember left positive, right positive. Who told? It's not like that. Remember these sign convention. Talking about magnification, magnification in lens I will tell, and I'm going to tell in mirror, okay? Lens and mirror. See, you will be expecting numericals on lens for mirror formula, that is 1 by f is equal to 1 by v plus 1 by u, okay? This is mirror formula. What's lens formula? It says 1 by f is equal to 1 by v minus 1 by u. Got it? This is lens formula. And what does magnification actually says, right? So magnification is how big the image is compared to object, okay? Magnification is hi divided by ho is equal to v by u. This is for lens, my dear students, but for the mirror, magnification is equal to HI by HO, where it is minus V by U. See, we've got minus formula over here. Derivation is not there. But remember, the different formulas what we use. Numericals, you will be having only one unknown, and you will be having kind of, okay, you'll be kind of having easy numericals on that. I hope you will be doing magnification, okay. Sir, this is the last live of physics session. Yeah, my dear, for the 10 CBSE physics, last live for this academic year, okay. Now, one more thing I have to talk about magnification. See, magnification, if magnification, okay, if magnification is positive, if we say magnification is positive, the image is erect, okay, it is erect, it is not upside down. If magnification is negative, it is upright, that is upside down. This is real, right? Upside down, that is inverted. What can we write? This is inverted. Inverted means we have got real images, and if the magnification is positive, we have got virtual images. Okay, sir, done. Can magnification also helps us to understand the size of the object? Definitely, why not? You know that magnification, okay, if you just, okay, positive negative only says whether it is real or imaginary, but remove the sign, take the magnitude. If magnification is 1, okay, what shall we conclude? Object is equal to image, okay, like 1 is positive, 1 is negative, like that. Yeah, whatever your question is, just focus. You can ask me once again, peacemaker, okay. So magnification is 1 means object, okay, HI is equal to HO, height of image is equal to height of object. But if magnification is less than 1, what can we say? Height of image is less than height of object. Imagine if the magnification is greater than 1, we say height of image is greater than height of object. HI is height of image, HO is height of object. Clear? Yes. Sir, in magnetic effect, difficult to determine the direction of force. That has been discussed. You can go back and see. First, we discussed that. So, this is about magnification. Talking about one last thing, the power of the lens. Okay, power, okay, of lens is 1 by focal length. Okay, focal length in meters. If you take focal length in meters, whatever power you get would be in diopter. That's the SI unit. Got it? So the SI unit would be what? Diopter. Okay. So diopter would be the SI unit of lens. So that's all for the first chapter. Going for the last part of the session, the last chapter which was left, human and colorful world. Any numericals? No numericals. Only theory. I hope you enjoyed this, because this will be what kind of last chapter. Okay, Prabhakar, focus. We have covered everything. Okay, last chapter. Now here the thing what they might ask you is different parts of the eye. Okay, so what's gonna happen with different parts of the eye is we have got cornea, pupil, anterior. Okay, I'll talk about this and all. Okay, see, the part which is not required I'm going to erase. Okay, just give me a moment. Okay, this part. Okay, now what is cornea? Is that cornea is the outermost layer of the eye. What does that do? That is going to save the eye from dust and other foreign particles entering the eye. Okay, so cornea is the gateway for the eye. That's a transparent layer. Okay, it's a transparent convex layer where most of the refraction happens. See here, that allows the light and most of the refraction happens. Okay, then it comes what's that lies between cornea and the other stuff, that is aqueous humor. Okay, so this liquid, what does that do? That provides, it's almost 99% of water, vitamins and all, that gives you enough vitamins and proteins that nourishes the cornea. Clear? I hope this is clear for you all. Next, going to the next part of the eye, iris, right? Well, talking about the pupil and iris, what is happening here is that this part, the center of the eye, if you look into the mirror, there'll be one more black dot. So that's pupil. So what does pupil does is that pupil is kind of, it's like gate. Okay, the light has to go inside of it. When you see very brighter places, this iris, okay, this entire iris is kind of makes the pupil small so that less amount of light goes into your eye. But when you go into very darker spots, this iris which gives the pigment of the eye, brown, green, blue color, that's kind of pulls this apart and the pupil becomes bigger, right? So this is what iris does, okay? Now, going to the next part, ciliary muscles. See, my dear students, ciliary muscles are those which controls the shape of the lenses. Whenever you're seeing far away objects, okay, what's going to happen whenever you're seeing far, okay? Whenever you're seeing far away objects, you know, the ciliary muscles are kind of, they relaxes. Whenever you're seeing far away object, what happens to the ciliary muscles? They relaxes. They relaxes, they become thin, and it will be able to focus on part of retina. We're going to talk what retina is, okay? And part of the, and then when you're focusing nearby object, okay, the ciliary muscles contracts, okay? It contracts. What does contraction do? It is going to bulge, okay? Bulge the eye lens, okay? Bulge the eye lens, thereby helping us with the vision of seeing something near, okay? Next, going to the next part of the lens. See, next comes vitreous humor. The eyeball is filled with a liquid that is also transparent. That's what we call it as vitreous humor. Without vitreous humor, eye will collapse. It's like balloon. Imagine you're filling water inside the balloon. What happens? The balloon bulges. If you remove the water, you puncture it, the balloon collapses, right? That's what vitreous humor also does. It's like provides nutrients to the eye and also helps to maintain the shape. Start with, cornea. Cornea is outermost layer. Iris, which gives the pigment to the eye. Pupil, opening of the eye. Aqueous humor, that's between lens and the cornea. Crystalline lens. Lens is when, kind of which makes rest of the part of the refraction after cornea. Ciliary muscles which hold the lens, which is kind of changing the shape of the lens. Retina is a part where rods and cone cells are there, which are going to help you to sense the colors and the brightness. Optical nerve takes the messages into the brain, right? Yes. Yes, great. Okay, now going to the next part, photoreceptors. Okay, in retina you'll be having something called as rods and cones. See, nothing is there here. Okay, well, technically no numerical is there, only theory part. You should know everything before you write the answer. So rods are like brightness. Rod help you to see the brightness, cone help you to see the colors. Okay, see how many colors do we have? We have only 3 colors: RGB, 256 shades of red, 256 shade of blue, 256 shade of RGB, right? Green, right? Mixture of those will be giving you billions of colors. If you can see billions of colors here, each dot, how many dots are there? I cannot count, so many billion dots are there. Those many colors are there. This is how the cones will be helping you to see different colors in the entire universe. Clear? Is it clear, my dear students? So how does this work on ciliary muscles and rods and cones? Okay, now see, whenever you're seeing bright light, the size of the pupil is reduced because of the iris. But whenever you're seeing dull light, the pupil becomes big with the help of iris, so that more of the light enters through that. Okay, thank you for giving me the confirmation, Indu. So quickly revising, cornea protects the eye outermost layer, and most of the refraction happens. Pupil opening through the eye. Pupil is controlled by iris. Iris not only gives you the color, pigment, but also controls the opening of the eye, how much light goes and out. Okay, then going to the eye lens. Eye lens is a crystalline part which can change the shape. Okay, power of adoption. Okay, now what's going to happen? The lens can become bulged or less with the help of ciliary muscles. If you're seeing distance object, ciliary muscles will relax, and if you're seeing nearby objects, the ciliary muscles contract, making the lenses more bulged. Retina, it is where the image is formed. Okay, so that's about the retina. Okay, retina has got rods and cones, where rods will be helping you to sense the bright colors, and and cones will be helping you to sense the colors. Okay, yes, I hope this is clear. Now Going to the next part, my dear students, talking about power of accommodation. Sir, what is power of accommodation? Okay, yes, the power of accommodation is like if your eye is able to see the nearby objects and far away objects clearly, that's what the power of accommodation is. Okay, now see here, he's focusing on nearby objects, so this is bright and rest all is blurred out. But over here, when you try to see the far away object, that is clear, this is blurred out. See, I can able to see both nearby and far away objects. That's what is power of accommodation. And I want to just give a shout out to everyone who is there in the live chat, responding to me and my comments. Thank you. I've got Aurora, Sensation, Prabhakar, Shiva, everyone, okay, Peacemaker, everyone, okay, thanks a lot, okay. So what's power of accommodation? Is the ability of the eye to see different objects at different positions. Okay, it's achieved by changing the shape of lens with the help of ciliary muscles. Got it? I hope this is clear, my dear students. Going to the next part, defects of the eye. See, eye is not good for everyone. They might be having some defects of eye. See, what happens in the defect of eye is that a normal eye, this is normal eye. What does normal eye does is that normal eye can see nearby objects and far away objects clearly, right? But a myopic eye, myopic is called as what, my dear students? It is short-sightedness, okay? It is called as short-sightedness, okay? Short-sightedness, okay? What happens with myopia is that we are kind of having the ability to see things which are near, but which are far is not able to see. Okay, so this is what we call it as short-sightedness. So what are the causes for short-sightedness? See here, the light rays are forming in front of retina. It's not actually clearly forming on top of retina, but in front of retina. This is why is going to happen. We are not able to see the images clearly. But just in case, if we try to introduce a diverging lens, okay, diverging lens, what's going to happen? The diverging lens diverges the light and focuses exactly on top of retina so that you can clearly see, right? So this is short-sightedness, okay. What are the causes? Corrective action. Shall I write it on the board? Yes, let's write it on the board, okay. So myopia is called as short-sightedness, okay. Short-sightedness, okay. Short-sightedness is also called as what, my dear students? It is myopia, okay. Myopia. So what's going to happen is that you are able to see nearby objects. See, short means nearby, okay. Nearby. Sighted means able to see. Able to see. What are you not able to see? The stuff which is far, you're not able to see, okay. Right. So what are the causes? What are the causes for this? There are many causes, okay. Causes. The first cause might be a bigger eyeball. If the eyeball is bigger, whatever it has to focus here is not focusing that. Eyeball is bigger, right? So we can say bigger eyeball, okay. Bigger eyeball. Or we can say it is more convex lens. That means the lens has become so convex that it is converging quickly, right? So convex or bulged lens, we can say bulged, okay, bulged lens, okay. Or there might be one more case, your ciliary muscles might not be working properly, right? Though ciliary muscles are weakened ciliary muscles, okay. Weakened ciliary muscles. So these are the causes, guys, for and myopia. Now talking about hypermetropia, can you see what is happening in hypermetropia? This is for normal eye, both are visible. This is for what? This is for normal eye, both are visible. But in case of hypermetropia, nearby is not visible, far away is visible. So hypermetropia is also called as far-sightedness. See, far away it's visible, nearby it's not visible. It's called as what? Far-sightedness. Okay, far-sightedness. So what is happening with myopia, hypermetropia is usually beyond the eye it is focusing. Can you see, whenever the object is kept here, it is happening beyond the eye. So only when the image is focusing on retina, it will be clearly visible, or else it won't be clearly visible. So what we do, corrective action is, this is a convex lens, that is diverging lens. We are going to use what kind of lens? A diverging lens for the hypermetropia. Quickly talking about hypermetropia. Shall we talk about hypermetropia? Hypermetropia. So what's going to happen is, it is called as far-sightedness. Okay, far-sightedness. Okay, what do you mean by far-sightedness? Far means which are very away. Sightedness, able to see. You're able to see which are far, not able to see in which are near. Okay. Pacemaker, I'm talking about presbyopia. It's very short. No, that's there. It's there in syllabus. Okay. Now, what's going to happen is causes. Okay. Causes is the opposite of it. See, the what might be happening is that, where did it go? Hypermetropia, right? What might be happening is, eyeball is shorter, so that the focus, it has to happen here, but the eyeball itself is shorter, right? It is happening like causes. Smaller eyeball. Okay, smaller eyeball. Next, what might be another issue? There might be a thinner eye lens, because it is not focusing prior, the focus is happening beyond, right? A thinner eye lens. Okay, thinner eye lens. Okay, next, weakened ciliary muscles. Again, here the ciliary muscles might be weakened, so you're not able to see that. Okay, weakened ciliary muscles. So these are the things which are kind of reason for hypermetropia. What is the corrective action? Remember, I just said the corrective action for hypermetropia is, we are going to use diverging lens. Diverging lens is kind of what did I write? Converging. This is not diverging, this is converging. Convex is what? Converging, right, my dear students? Okay, converging. Okay, it converges priorly. Okay, yeah, the focal length decreases with this lens, but the defective eye focal length is increased. Yeah, right. Okay, now talking about presbyopia, it's the combination of myopia and hypermetropia, both near and far sightedness. Okay, both near and far sightedness. Okay, so now what kind of lenses are you going to use? You're going to use such a kind of lens where, while seeing far away objects, you want what? Concave, right? See here, this part you're going to see, whenever you're using spectacles, I'm using spectacles, I use the upper part to see far away objects, right? Whenever you don't get to see far away objects clear, far away objects are not clear, what kind of lens are you using? You're using convex, right? So here, this part you'll be having convex lens. Okay, but whenever you are reading nearby objects, when nearby objects are not visible, see here, when nearby objects are not visible, we call myopia, right? Or guys, one second. All right, here, see, what happens is that for presbyopia, both myopia and hypermetropia, both are there. Whenever you're not able to see far away object, that is what? Myopia or hypermetropia. So myopia, you use what kind of lens? It is concave lens, right? So here hypermetropia is happening, nearby is not visible, so it is convex lens. We call this as bifocal lens. Okay, bifocal lens. Okay, or you can also use progressive lens. Okay. Okay, great. Okay, now bifocal lens or two focal lens are there, that's why it is. Okay, so far is not visible, that is it's like short-sightedness, right? So you're going to use concave lens, here convex lens. This is presbyopia. Okay, now sir, is there a question on refraction through glass prism? Yes, my dear student, it is there. How to use that? Well, let's see. See here, what is happening is that the incident light ray, if you focus here, everything will be super easy. Okay, just keep focusing and focusing. See, the light ray is coming like this. Can you see the light ray is coming? Yes, the light which is blinking, you have to see, that is incident light ray. Whenever whatever I'm saying that blinks, okay, the incident light ray is entering from the air into the prism. Well, the air is rarer medium, glass is denser medium. So rarer to denser, how should it bend? It should bend RTD, right, towards the normal, right? If this is the normal, it is bending towards the normal. Away means like this. This is towards. Okay, from here, prism is glass, right? So uh, prism is glass, and what's going to happen over here? Denser, air is rarer, right? This is how it is. So this is one refraction happening. Now from denser to rarer, it should bend R. See, DAR, away the normal, right? See, if this is the normal, it is bending away the normal. So the emergent light ray is bending away the normal. This is how it happens. Got it? So incident light ray is PQ. This is what PQ is. Refracted light ray is FS. This is the refracted light ray, emergent light ray. Okay. So EF is the refracted light ray. What is A, sir? A is the angle of prism, my dear student. Now, what is angle of deviation? Can you see D over here? Imagine the light ray was supposed to go like this. Light ray was supposed to go like this. But is it light ray going like that? No, it has deviated, right? It has deviated. So it has deviated like this. If you measure the angle, how much it has deviated, that's what gives you the angle of deviation. Got it? Okay, is it clear? Hope this is clear how refraction happens. If they ask you in exam, you have to write all these, okay? Angle of incidence, see, angle of prism, angle of incidence, deviation, angle of emergence, refraction, everything, okay? I hope this is clear for you, my dear students. And what does this do is that whenever a white light is coming, can you see this is a prism, right? A white rays entering. The prism disperse, okay, splits the white light into its constituent colors. Dispersion means splitting, okay? What does this dispersion means? Dispersion is splitting, okay? What is dispersion? Dispersion is splitting. Splitting of light into its constituent colors. That's what is dispersion, okay? Splitting of light, white light, okay? White light into its constituent colors. Constituent colors is what we're going to call it as. What, my dear students? That's dispersion. See how many colors we have? White light is made up of VIBGYOR, 7 colors, okay? So this is how dispersion happens. So how does dispersion happen in nature? Well, how to write? Formation of rainbow. Dispersion in nature. If they ask you a question, you should write about formation of what? Of rainbow, right? So how does the rainbow forms? See, we have two things. One rainbow, one double bow. Rainbow is the primary one. Double bow is the different one, which I'll explain, okay? But can you see the colors of rainbow? Is it VIBGYOR or the different? Let's see. First you can see red, right? So VIBG, okay, let me write it a bit small, okay? The pattern of, guys, the color of rainbow is not VIBGYOR. If they ask you if you write VIBGYOR, no, wrong. Can you see how rainbow is forming? Red is at the top, right? VIBGYOR. It's like ROYGBIV. Like Roy GBIV is the pattern of formation of rainbow. It's not VIBGYOR. Because you can see red is at the top, violet is at the bottom, okay? Technically, dispersion happens like this itself, okay? Let's see how the dispersion happens, okay? Now, whenever the light enters a water droplet, it might be acting like a glass prism, right? So what's going to happen in glass prism? There will be dispersion of light. So the light split into its constituent colors. That's like scattering, dispersion of light. So the dispersion happens here. If you can see, internal reflection is also happening. So the internal reflection happens, and here again the refraction is happening. So what's going to say? The formation of rainbow. the white light enters a water droplet, and the water droplet will be acting like a glass prism. The glass prism refracts and disperses the light. Dispersion is splitting of light into constituent colors, and internal refraction happens, and then again refraction happens. Sir, you said the rainbow is not VIBGYOR, but here it is VIBGYOR. No, are you wrong? No, I'm not wrong, because this is because of one drop. Rainbow is not because of one drop. Rainbow is because of many drops, right? So the formation of rainbow is, the color, the order is like this: ROYGBIV. Okay, clear? And one more thing I wanted to tell you. See here, how does the splitting happens means, whenever the light with least wavelength splits more. See, violet has got low wavelength, okay? Wavelength. The one with low wavelength bends the more, okay? It bends more. The one red, okay? The red with more wavelength, it is having kind of more wavelength. So what happens? The red with more wavelength, it does not bend more. As simple as that. Got it? I hope this is clear. Okay. Yes. So this is about formation of rainbow. Sir, rainbow you discussed. Okay, rainbow is done. What is the other thing? That is double bow. What happens in double bow is, the other part of the refraction happens in the other way. See, here the white light is entering from the top. If the white light enters from the bottom, whatever happens is the other part, that's like double bow, which will be having VIBGYOR pattern. Clear? I hope this is clear. Formation of rainbow. Question will be asked. Okay. One last part is there, atmospheric refraction. How to understand? See, I'm going to explain it with such a simple example. Imagine this is Earth, right? Earth has got what? Different layers of atmosphere, right? What has Earth has got, my dear student? It has got different layers of atmosphere. One layer is over here. You have one more layer, and you have one more layer. Okay, clear? So like this, you'll be having how many layers? Many layers you'll be having. What is the application of atmospheric refraction? Let me write and then I will explain. Okay, early sunrise or late sunset. Let me explain early sunrise for you. Okay, early sunrise. Okay, or let's say sunset, so you will be able to understand it quickly. Okay. Late sunset. Okay, I'll write both. Early sunrise or late sunset. Late sunset. So what's happening is that, imagine you are standing on top of a tall building. Okay, you are standing on top of a tall building. Okay, now what is happening is that you are somewhere around here. Okay, now what is actually happening is that, let me go ahead and help you. This is sun. Imagine, what is this? This is our sun. This is our sun. Now the light rays will be bending in such a way that see, it bends, light ray comes here. Okay, it bends. Okay, this is a light ray. Okay, let's say you're standing over here. Okay, you're standing not on top of building, you're just standing over here. Okay, and then what happens to the light ray? Light ray again bends, and light ray bends. Okay, the light ray is bending, another light ray, it bends. Okay, so this is how the bending is happening because of atmosphere. So what does atmosphere does? We have two different medium, of course refraction happens. Our eye thinks that light is a ray. It does not bend according to our eye. So it thinks, oh, sun should be kind of over here. This is where the sun is. This is what our eye thinks. So do you think the eye is actually thinking right? No, right? So the sun actual position is below, but eye thinks the sun has already risen. So this is what we say early sunrise. This is apparent position. Okay, this is what apparent position. Okay, actual real position of sun is down, but because of atmospheric refraction we should write it's that. Okay, apparent position, this is real position, this is real position. Guys, with rainbow, I know lots of confusion is there. Even if you see the actual rainbow or Google the images, what you will get? You will get this, not VIBGYOR, ROYGBIV. That's how you see rainbow, right? Rainbow is because of what is happening at the final stage. So that's how it is, okay? But the refraction is happening in VIBGYOR. Final rainbow is ROG format. See here, don't get confused. See, with one droplet, it is VIBGYOR. Peacemaker, listen. With one droplet, it is VIBGYOR. Okay, I understand. But do you think it is because of only one droplet it is happening? Refraction is happening because of only one droplet? No, right? Refraction is happening because of millions of droplets. And in fact, you Google any images and see, this is kind of bit complex concept, but for your level, this is this much. There is some angle which makes 45 degree between line of sight. Lots of things is there, okay? So you see that general sense, okay? Of course, you have to get marks just in case they did not give marks. You can appeal, okay? Right, I'm here with you. Right, going to the next part. So atmospheric refraction happens. Now, see, because of atmospheric refraction, the stars twinkle on Earth, but on Moon we do not have any what atmosphere. So on Moon the stars kind of does not twinkle. Okay, talking about the last part of today, why sky appears blue on Earth. The question is not completed. Why sky appears blue on Earth? Okay, why sky appears blue on Earth? Very simple. The constituent, the particles in the atmosphere are of such a size that it absorbs the lower wavelength and emits. That's what we call scattering. Very good, Kriti. Okay, the particles in Earth's atmosphere. Okay, atmosphere. Okay, scatters lower wavelength. Okay, what does that do? Scatters lower wavelength of light. Scatters lower wavelength. What does scattering means? Guys, scatter means absorb and re-emit. Okay, if you have doubt what scattering is, scatter is absorb plus re-emit. Okay, absorb plus re-emit. Scatters the lower wavelength, which is having lower wavelength, like from blue, indigo and violet. Okay, scatter means it absorbs and re-emit. When it absorbs only blue light and re-emit, what's going to happen? The sky indeed looks blue, right? So because it is doing that with only blue light, right? Scatters wavelength, lower wavelength, like blue, indigo and violet. Hence what happens? Hence the sky appears blue. It is not blue, it just appears blue. Okay, great, sir. Understood. One last thing. Why danger sign uses red signal? Well, the Earth atmosphere is not having the capability to scatter higher wavelength of red. Okay, that's why in danger signals, in the tail light, we call this as tail light, which is there at the back of the car, or the laser light of snipers. So what happens? It's like it doesn't scatter, it reaches wherever you want it. So that's why it's scatter least. For the dangers and all, we are going to use that. So that's all for today, my dear students. I hope you all enjoyed this session. All the very best for your final exams, which is there in 2 days. Any doubts, go to the recorded part, watch it. I have super confidence in you. You all will be able to do it. So that's a wrap. Have a good night. Do not stress yourself. Eat healthy, stay healthy, and do better in your exams. See you all in the next part whenever I'll be meeting. Thanks for staying with me. All the very best. You all can do it. Take care and tata. See you. Bye-bye. Have a good night.